Good afternoon, everyone. I want to welcome you to this celebration of the anniversary of the 90th birthday of Carl Sagan. My name is John Silicano. I am currently the interim provost at Cornell. I'll be in this role for another 6 weeks, and then the new provost, Kavita Bala, will step in. Kavita, can you just wave so people know who you are? So I will be done. I'll be done on December 31st. Kavita will start on January 1st. That'll be very good news for both me and the university to have that changeover. But I'm delighted to be here. This is my last public appearance, and I'm grateful for that. The other one I did recently, so I'm very happy to be able to do this, and also the opening of the Lab of Ornithology. I was a very strange child, and the only thing I cared about, the only friend I had was the girl next door. The only thing we cared about was birds and stars. And we didn't have any other friends, we didn't need any other, but those were the two things. And then I was so fortunate to end up at Cornell with the Lab of Ornithology and the home of Carl Sagan. So I'm very grateful to be able to introduce today's events. I'm particularly happy that our Emmy and Peabody Award-winning writer, producer, and director, Ann Druyan, is here with us. Professor Sagan's widow and longtime collaborator, and she will be able to join us and will be speaking next. One of the weird things, some might say it's a benefit, but I think it's just weird of being the provost, even a temporary one, is you get a speechwriter. And a speechwriter has written a long, long list of things I should say in introducing this event and talking about Carl Sagan and about Ann. Very long list. I was working on it last night. I've decided sort of on the spur of the moment not to read it for 3 reasons. One is that even though I'm a lawyer and a law professor, I have always had difficulty, as you'll see, reading in public. This is attributable to the nuns at St. Patrick's Elementary School. There's a sad story around that still lingers. The second is you don't need me to introduce this event. If you don't know who Carl Sagan is, you're in the wrong auditorium. But here's the third, is that while I was doing this last night, I got a note from Kavita Bala just saying that she would be attending today. And in her note, she spoke very briefly about the impact that Carl and Ann had had on her life through all of their work. And I'm just going to read that note because it really says what all we really need to know. We could go through all of the accomplishments, but I've gotten Kavita's permission to read this. But she says, I saw Cosmos when it came to India, much later than the release in the United States, in the mid-'80s. It blew my mind. Not only did it introduce me to the beauty of science, the mystery of space, and set me on my path to becoming a scientist. It was my first exposure to Bach, and it instilled in me a lifelong love of classical music. The impact that Cosmos had on so many of us from the former third world countries is hard to convey. I know that many immigrant fellow scientists in this country who will say what I say, Cosmos changed our life trajectories forever. And I think that captures the full sum of the work of Carl and Ann. So we're celebrating Dr. Sagan's birthday with scientists from the Carl Sagan Institute, whose work has carried on Carl Sagan's vision and legacy since 2015. This is an interdisciplinary institute. It was founded to discover life in the universe and explore other worlds within and outside the solar system, and to understand how they formed and evolved and whether they could harbor life. I'd like to thank our colleagues who have sponsored this event, Lisa Kaltenegger, Professor Kaltenegger, who's the faculty director of the Carl Sagan Institute, thanking the College of Arts and Sciences, Dr. Sagan's academic home, and the college's Unplugged series, which brings research and creative works into the public sphere. Also, the College of Engineering and the College of Agriculture and Life Science, who have partnered with Arts and Science for this event, and whose researchers are also engaged in a multidisciplinary work at the Carl Sagan Institute. Gillis Lowry, recent graduate and now staff member and science communicator from Cornell, and the Cornell Astronomical Society, which is the student organization that has run public observing nights in the observatory for 50 years. Now, my pleasure to introduce Ann. Again, there's a very long list, and I will read some of this, though certainly not all of it. Ann is the Emmy Award-winning writer, producer, and director. She resides in Ithaca. She was the creative director for NASA's Voyager interstellar messenger, which is still speaking to us from 47 years later. With Carl, she was the co-writer of 6 New York Times bestsellers, including Comet, Shadows of Forgotten Ancestors, The Demon-Haunted World, Billions and Billions, we all know that, and The Variety of Scientific Experience. She was a co-writer of the original Emmy and Peabody Award-winning TV series Cosmos, A Personal Voyage. She was the co-creator and co-producer of the feature film Contact, starring Jodie Foster. She's produced multiple documentaries, including Cosmic Journey, the Voyager Interstellar Mission and Message, which was nominated for the Emmy Award for Outstanding Science, Technology, and Nature Programming. She was the program director of the first solar sail deep space mission launched in 2005, currently producing 2 major films and is at work on an additional project. And again, the list goes on and on. The final thing I want to note, which is just lovely, is that there's asteroids named after her and her husband that are in a perpetual wedding ring orbit around the sun. Welcome, Ann, and thank you all you've done for this.
I can't thank the Carl Sagan Institute and Lisa Kaltenegger and Gillis Lowry and all of the people who made today possible enough. Talking about Carl is one of my favorite things to do, thinking about him. I am the very lucky recipient of love for Carl from around the whole planet. A day doesn't go by when someone doesn't reach out to me and tell me, as was just said today in John's lovely introduction, that their life was affected by something that Carl did, that the whole trajectory of their life was enhanced and broadened by something Carl did. The topic of my little brief talk today is the gift Carl gave us. And I know I declare my bias beforehand. It's a very great one. But when I think of Carl, I think of his life as a masterpiece of citizenship, of a person who dreamed of becoming a citizen of the cosmos, but who was first and foremost a citizen of Earth. I think of the things that he did that were not promoted and that were not talked about. I think of his trips to the immigration and naturalization ceremonies to inspire new citizens to question authority. I think of his love of the Bill of Rights and why he felt so strongly that it was one of the 2 greatest error-correcting mechanisms humans had ever devised. The other one was the methodology of the science. And he loved science and he loved the Bill of Rights because he thought, here, as a species, we know our tendency to dominance hierarchies. We know our tendency to push others of our own species around. The Bill of Rights is that error-correcting mechanism that prevents the alpha male, or whoever wishes to dominate, from hurting those of us who have the least power. And that is why Carl would go where the people were to spread the message of science. He believed that the more that we knew of the wondrous universe revealed by science, the more we would feel a sense of humility about the fact that our story is 4.5 billion years long, that we are all links in the chain of generations, and that generation, that chain of generations links us to every living thing on Earth. And most of all, that we are not the children of a chronically disappointed parent, but instead star stuff, formed in the fiery hearts of distant stars, every one of us equally, and all life equally, and that is a source of wonder and awe. And what is kind of sad but meaningful is that the only people who really gave him a hard time about this were other scientists. The community of science was somehow offended that science was not going to continue to be an elite priesthood for a tiny few. But Carl really loved the concept of democracy. And as he warned many times on this campus and all over the world, to have a civilization dependent on science and high technology, and to make it so that only a tiny few could understand how it worked, was a recipe for catastrophe. And when I think of the demon-haunted world, I have to say, I think of this past week. But life is the greatest writer of all, because here we are in the aftermath of what was for many of us a source of heartache, celebrating someone whose life exemplifies what we need to become in order to endure. One of the things Carl would do was to speak to the teachers of the public schools of Tompkins County on the night before school would begin. And he would tell them, and speaking from the heart, he really meant it, what a sacred undertaking they were participating in, to have this lever arm on the future, to be able to fan that spark of curiosity, those little children who are perpetually asking why, to honor their questions and to make them lifelong questioners, searchers, like the generations of science. And it's that degree of citizenship that I ask all of you to summon up in yourself if you, like me, have had a tough week. And that is to reach out. I see the physics bus outside the Space Sciences building parking lot. And I think, yes, that is what we need. That is exactly what we need. We need to reach out, and we need to embrace our fellow citizens. And whatever gifts we have, whatever knowledge we have, whatever strengths we have, we need to share them. Because that's exactly what Carl would be doing. He was derided for going on the Tonight Show and writing for Parade magazine, the Sunday supplement that went into the nation's newspapers. Why did he do that? Why did we make Cosmos a television show? Because we wanted to reach each and every person on Earth, because this birthright this little picture of the universe that we have been able to assemble belongs to everyone, and anyone who has any degree, even the tiniest understanding of how powerful it is, can experience a moment of human self-esteem, which is what we need now more than ever before. I'd just like to close with a thought about why I think Carl, who was completely human, nothing supernatural about him, all of the foibles that we all have, but why was he so special? I think of the fact that when the Voyager mission was being planned, Carl was in those meetings talking about the mission trajectories with the scientists and engineers, plotting the course of Voyager, thinking of what planetary and what rendezvous with the many moons of the outer solar system, how they could maximize and see as many worlds for the first time up close. And then when the data came in and the pictures came in from the outer solar system, Carl was upstairs at JPL with the imaging team. And he was contributing to the analysis of what that data and those pictures meant, what they were learning for the first time about these worlds. And then in between the planetary encounters that would take place every 2 years or 3 years, Carl was going to Washington, D.C. and pleading with the NASA administrator that Voyager 1 would take one last picture after all the pictures were taken, that Voyager 1 would look homeward and see our world and the worlds of the sun as we had never seen them before. Not the frame-filling Apollo vision, which in itself was a sea change for our civilization. Not that Earth filling the screen, but the one pixel Earth. And without fail, they would say to him, Carl, what's the scientific virtue of seeing the Earth as a single dot? You know, it'll fry the cameras if we look back towards the sun. This is after all the pictures were taken. They said no to him for 9 years, but he never gave up. And ultimately, he succeeded in seeing our world as it really is. Tiny, fragile, tiny, a small, tiny world. And it was Carl who could do all those other things and then be the person who could write about it in such a way that he could pierce the frozen sea inside of us and make us look in wonder at ourselves and each other and realize how pathetic and how futile our conflicts are in the face of the vastness of space and time. Well, more about that later. But I just want to say that I know that Carl would be so thrilled that you came today, and that so many people around this little planet care so deeply for him. I plan to use the inspiration of spending 20 years with him and knowing that all the love that he received was really, if every one of those people had known him the way his family did, they would be even more in awe of him as a human being, as a father, as a husband, as a son, as a friend. So thank you. Your love of Carl could not be better placed. And I'm so excited to hear the rest of this program and the new knowledge. that the Carl Sagan Institute and his friends have assembled, he would have loved this. He would have loved the research aspect of it, but he also would have loved its efforts at public outreach, at connecting with as many people as possible. So today, it is my honor to introduce the great Lisa Kaltenegger. I'm going to enumerate her many achievements, but before I do, I just want to say none of us would be here today. Yes, she's the director of the Carl Sagan Institute, but she's also the founder and the person whose tireless activities has really made this wonderful institution possible. And so now, hold on one second, I'm going to find the details of her introduction, which I had thought I had lined up here. And just give me 1 second, I feel very silly. Hold on one sec. Forgive me, guys. I got a little too excited about being with you today. Lisa, I'm so sorry. I had this whole thing here, and I can't seem to find it.
That's okay.
Well, Lisa has won so many prizes. Let me just tell you what I remember from it. Lisa has worked at NASA, at the European Space Agency. She has taught and conducted research throughout Europe, at Harvard, here at Cornell. She's the author of a fantastic book called Alien Earths, which I urge you all to read. And she has received too many awards for me to remember, and I'm just overjoyed to know her and to be able to introduce you to her today.
Thank you so much for coming, and thank you so much for being here with us to celebrate what would have been Carl Sagan's 90th birthday. It is my great pleasure to be here at Cornell, and actually coming to Cornell. Carl Sagan had a big reason for me to come here, because a long time ago, he already realized that if we want to find life in the universe, an astronomer can't do this on their own. A biologist can't do this on their own, and I'm not dissing any of my colleagues who are amazing. We have to reconnect, because luckily, we live in a time where one person cannot know all of science anymore, because luckily there's so much to know. And so it is my great pleasure to bring you just a little bit in these short talks by many different people that are fellows at the Carl Sagan Institute here, some new insights and what we have discovered. But I wanted to say, whenever I look up at the sky, I wonder what Carl Sagan would have thought of all these new worlds we have discovered. And I wish I could run into him in our coffee corner on the 3rd floor. But I do live in his office now, so I get to look outside and see the campus like he would have seen it. And sometimes it helps me to pause on an incredibly busy day to just think, maybe he would have just stopped for a minute too and thought about the bigger picture. And that grounds me, because the search that I'll share with you has just become the most exciting. Because we have now found more than 5,700 planets circling other stars, and we have 10,000 more that we just have to vet still. Did the detector do what they did? Did the telescope work? So we have thousands and thousands of new worlds circling other stars on our shore. And of course we can get there, but light is a messenger. And throughout history, astronomers have captured light and read the information encoded in light, because light and matter interact. And so when you look at this amazing image that the biggest space telescope we have launched yet, the James Webb Space Telescope, has taken of the pillars of creation, it's a beautiful image. But once you analyze the light, you realize that there are stars being formed there right now, emerging and starting to burn their fusion in the core. So it's so much more than just a gorgeous image. It's a stellar nursery that we get to watch, where stars and planets are just being formed. And I told you that we know that there are 5,700 planets orbiting other stars. But really, we also know how bad we are at finding them, because planets are so small compared to big stars and bright stars. So from the number we find, we can tell you that every second star must have at least a planet, and that every fifth star has a planet at the right distance, not too hot and not too cold, and small enough to be a rock. And with 200 billion stars in our galaxy alone, that means billions and billions of possibilities. But I can find signs of life in the cosmos on my own. And this is why it is such a pleasure to come here to Cornell and create the interdisciplinary Carl Sagan Institute, where people from more than 15 departments share their knowledge, and they are thinkers with different background, creatively trying to find life in the cosmos and make the toolkit for us to not miss it if it's out there. And from some of those you will hear today, these are the people that you see in the blue boxes, and I hope you'll get a little bit of the excitement that is currently in the search. But you'll also see that we have musicians and performers here, because this is excitement that we love to share. But how do we do this? And you'll hear a bit more about this in the next talk. Right now, we can only look at the air of a planet as small as ours if it by chance goes between us and its star, and the light from the star crashes into the atoms and molecules of the air of the planet before getting to my telescope. And that residual light missing, so the light that's missing when it gets to my telescope, tells me what chemicals it encounters on its path. Because signs of life are written in the air or in the light of a planet. But this is at the verge of technical possibility. This is incredibly hard, even with the biggest telescope. And so even the James Webb Space Telescope is going to have a hard time getting to that precision for us. But for the first time, the search has changed from impossible to possible, trying to find life on planets circling other stars. And you'll also hear about the amazing discoveries in the solar system and how we're trying to find life here. But for a planet circling another star, another Earth, this is basically how it would look like if it were like the Earth. You see that there's some light missing. It's not just the solid line. And that light missing is the energy missing because light hit an oxygen molecule, because it hit a methane molecule, because it hit a water molecule and made them swing and rotate. And so the light didn't get to my telescope. And that's what we're looking for. But of course, another planet doesn't have to be a carbon copy of modern Earth. It could be very, very different from what we know here. And so we're building a light fingerprint database of possible habitable worlds, how their air could look like, because there might be a biosphere changing it as well, how their surfaces could look like because biopigments color them. And we have a lot of challenges, opportunities, and adventures. And it is my pleasure and my enormous privilege to have such incredibly talented, but also such kind, excited, and enthusiastic colleagues here to do this work with me. And we all, one way or another, were inspired by Carl Sagan and his way of seeing the cosmos and teaching us how to see. And with that, thank you very much, and we'll go to the next talk. And so it's my pleasure to introduce Professor Nicole Lewis, who's another professor at the Astronomy Department, but also at the Earth and Atmospheric Science Department, and one of the experts in the whole world of characterizing planets around other stars.
Well, thank you all. It's wonderful to be here this afternoon. And I'm going to sort of lead off of what Lisa's already told you and talk a little bit about how we're using the James Webb Space Telescope, the biggest telescope we've ever put into space, to sniff exoplanet atmospheres and figure out what they're made of. But I wanted to first start with a little homage here. More than a decade ago, I was among the first few classes of Sagan Fellows. So this was a new fellowship that NASA had put forward, and they formed this fellowship to help sort of launch the careers of people who were interested in studying exoplanets and for the search for life. Now, myself and my colleagues in this picture here have all gone on to actually be faculty and researchers at various other places. But I just want to say that this was transformational for me in my career, and I am thankful that I can call myself a Carl Sagan Fellow. So, as an exoplanetary scientist, I spend my time thinking about how to answer the questions, how did we get here? As in, how did the solar system form, and how did the Earth come to be, and of course, come to host life? And of course, that leads to then, are we alone? How many other times did the magic that created our solar system, and of course, gave rise to the Earth, occur in other places in our galaxy and beyond? Now, as Lisa mentioned, we've now found nearly 6,000 confirmed exoplanets, with thousands more that are just waiting to be, told they're not false positives. But what I want to highlight is that this field really is quite young. We detected the first exoplanet around a sun-like star in 1995. I think most of the people in this room were probably alive then. Okay, yeah. So you've lived through the detection of the first exoplanets. We've always known that there should be planets around other stars, but now we have confirmed it. And what we've found is that, in fact, exoplanets don't look a lot like the planets in our solar system. We found that most of the exoplanets that we know of to date are, in fact, planets that are unlike anything in our solar system. They are about the size of somewhere in between Earth and Neptune, and we call them sort of mini Neptunes or super Earths. This came out of the Kepler mission, but now we know that there are lots of planets out there for which we don't have solar system analogs, and that's really opened our minds into thinking about how we study planets beyond our solar system and extend the context of what we understand from the planets we live and live near. Now, it's great that we know that there's 6,000 exoplanets, but I want to go beyond just saying, hey, there's exoplanets, and I want to know what are they made of and what is their air like? We want to know if they're big hunks of rock or iron, are they big gas balls? And then we want to know, what is in their air? Is there something indicative of potentially their surfaces being habitable or in fact inhabited? Now, I spent my early career working with data from the Hubble Space Telescope and the Spitzer Space Telescope. Both of these missions were launched well before we had 6,000 exoplanets. They were never designed to do this type of science. And so myself and others like me have spent a lot of time sort of retrofitting our observational strategies and also the data from these space telescopes to learn a lot about exoplanets. In particular, we've been focused on planets that are sort of the size of Jupiter, but orbit very close to their host stars. We lovingly refer to these as hot Jupiters. And so we were able to study hundreds of these types of planets and some smaller ones as well with the Hubble and Spitzer Space Telescope. But with the James Webb Space Telescope, we were able to actually think about how to observe these worlds well before the telescope launched. And so we were prepared to hit the ground running with the launch of JWST. And now with the increased capabilities of JWST, we are likely going to look at more than 300, possibly 500 or even 1,000 planets in great detail and understand what they're made of and what their air is like. Now, I got the best Christmas present I could have ever got on December 25th, 2021, and that was the perfect, more than perfect launch of JWST. The launch was so perfect that the mission now looks to have a 20-year lifetime. And so this is something that I'm really excited to be doing for the rest of my career. And so with JWST, one of the first things that the telescope looked at as part of the early release observations was the hot Jupiter WASP-96b. Now, this system was selected, it was in the right place at the right time, but it's also one we've studied before. And we were able to actually capture the event where the planet passes in front of its host star as seen from Earth. And so what you see is a dip in the light from the combined system, so this is the relative brightness as a function of time. And from this dip in the light, we can actually, just from simple circular geometry, figure out how big this planet is. Now, we already knew how big this planet was. We knew it was a Jupiter. And so what we wanted to do was actually to take that light we had just measured and spread it out into a rainbow. There are a lot of spectrographs on JWST, and they allow us to take that light and to assign it to different wavelength ranges that then allow us to sort of sniff the atmosphere to figure out if the atmosphere has things like sodium or potassium or maybe sulfur species, carbon dioxide, and water. And so using JWST, we spread that light out we got from WASP-96b. And so these are those observations. And in spreading the light out, we were able to see, again, these absorption features that Lisa mentioned before. And we know that these are all due to water in the atmosphere. Now, we weren't surprised that there was water in the atmosphere. We kind of knew that that's what we should see. But what we were more surprised about was the precision with which we were able to measure those water features. 200 parts per million is what we're measuring here. This is a 5 times improvement from what we were able to do with the Hubble Space Telescope. We are looking at tiny, tiny drops in a very large bucket in order to make these measurements. Now, JWST not only looks at planets as they pass in front of their host stars, they also take pictures of planets. There are several coronagraphs on the James Webb Space Telescope, and these instruments block out the light of the star, which is very, very bright, so that we can see the fainter planet next to it. And so here we have some pictures taken of the planet HIP 65426b in different wavelength ranges. And so we can measure the different colors of this planet. And that, again, tells us something about what's in its atmosphere and also its temperature. We can again look at these planets where we can take pictures and then spread out their light. And so one of the early observations with JWST was of what we call a directly imaged exoplanet. And we were able to spread its light out and detect everything from water to carbon monoxide to methane to these silicate features right here. So these planets have clouds in them, but they aren't clouds like the ones you see outside. These are clouds made of rock. This was also the first time that we were able to successfully detect carbon and sulfur-bearing species in exoplanet atmospheres. And so one of the first things we started to see as we spread this light out from different exoplanets is that there were these booming features out here in the infrared from carbon dioxide, and then right next to it is this sulfur dioxide. Now, the carbon dioxide was not totally unexpected, although it has shown up in a lot more places than we thought. But we did not expect to see these sulfur-bearing species. And this is indicative of photochemistry happening in these planets' atmospheres. It's also great if we want to go hunting for volcanoes on these planets. Now, coming back to those rock clouds, one of the things we were able to do early with JWST was to look in this very particular region of light, this wavelength of light, where the silicon and oxygen in these rock species actually do a little dance, as they say. And we were able to detect, in fact, very, very small snowflakes of quartz in the atmosphere of the hot Jupiter WASP-17b. And so in other words, you're not going to have a white Christmas from, say, water or ice, but you're going to have a white Christmas from quartz crystals falling from the sky. Now, going beyond sort of these giant planets, these hot Neptunes, we've been able to look at smaller planets, again, these sub-Neptunes, the most numerous type of planet that exists out there in our galaxy. And again, we've been able to detect a broad range of species, including methane, carbon dioxide, and then start to see hints of these things like dimethyl sulfide, which is thought to be a biosignature in many contexts. So again, we're starting to see key signatures of perhaps biology in these atmospheres of these sub-Neptune, these gas giant worlds. And finally, we've started to look at, in fact, Earth-sized planets. So this is observations of a planet that's only just slightly larger than Earth. It is quite a bit warmer, but what we've been able to do is, again, spread that light out and take a peek into its atmosphere. And so what we're seeing right now is, again, we're trying to distinguish whether this planet is water-rich in its atmosphere, so maybe having a lot of steam around it, or if we're still seeing signatures of the star imprinted onto this planet's atmosphere. There are hundreds of hours of observations with JWST that are devoted to looking at Earth-sized planets orbiting primarily small M-dwarf stars, hoping that we get some idea of what's in their atmospheres. And so while we don't have a definite detection of an atmosphere around an Earth-sized planet with JWST, that is coming sooner than you may think, so stay tuned. And so JWST, just in the first 3 years of observations, has really revolutionized exoplanet science and is helping us take those next steps to really answering that question, are we alone in the universe?
So, and with this taste, to go and see what's possible with the James Webb Space Telescope now and what will be possible soon, stay tuned, as Nicole said, I would love to take you now closer to home, into our solar system, because one of the fellows of the Carl Sagan Institute is Professor Brittany Smith, who is one of the experts of trying to find life in our solar system, especially on the small icy moons. And she also has a lot of love for our planet, and she tries to protect it at the same time as trying to find life out there.
All right, hi friends. So we're going to come a little bit closer into our own cosmic backyard, the Earth. So this is the Earth as I choose to look at it often, which is from below. So this is a picture of our robot I'll introduce you to in a little bit, working under the sea ice outside of McMurdo Station, which is possibly my favorite place on the planet. But for some reasons that we should care about this, in fact, getting back to Carl Sagan and how remarkable he was, I think were his thoughts on how connected humans are with the entirety of the cosmos and even with our own planet. And so I really loved some of his thinking on this subject, and here he's starting to talk about what we now refer to as Earth system science, which is the idea that the Earth and its entire population, humans, any organisms, the plants, the atmosphere, that it functions as a system and that we're all connected. And that as a part of that experience, it's our duty to protect it. And so, as Ann mentioned, some of the great work that he did was protecting people and protecting our planet. And so I'm going to tell you a little story about how thinking about space brings us closer to our own home. So this is my personal scientific hero, and this is Galileo. And so Galileo built one of, or if not the first telescopes in about 415 years ago. And if you have ever looked through a pair of binoculars, if you were to take one of those binoculars out, then you would be looking at the universe the way that he did. And what he did was remarkable. You should read his first paper, what an opener, or his first paper with a telescope. And what he did was to point it at the moon and say, my gosh, the moon is a planet. There's mountains, there's valleys, there's scarps, there's features that remind us of our own planet. He looked inward, then he looked outward. He said that there were so many stars in galaxies that you could see star clusters that had so much more happening in them, not galaxies, but clusters. And so he really looked across the entire system. And he said, now put all of that away, and I want you to focus on this thing that's happening in the outer solar system. And what he noticed were these pictures that he's drawn up here. So those are pictures from his original journal and from the publication, and I have it tattooed here on my wrist, which are the original observations of these 4 points of light moving around the disk of Jupiter, right? So for all of humankind, we had known that there were about 7 moving objects in the sky. We could see that Jupiter and Mars and Venus were different, but we couldn't see what was just around them. And so for the first time, we had these 4 points of light, and he noticed that as you watched them from night to night, the number of those objects and their positions would change. And eventually figured out there were 4, watched them move around over the course of about 3 months, and revolutionized everything we thought. And the reason for that was that at the time, the conventional wisdom was that the Earth was not only the center of our solar system, but it was the center of the universe. And with observations like these, he flipped that upside down and showed us that the Copernican version really was right. That not only was the Earth not the center of our solar system, but not the center of the universe. In fact, we're not the center of everything, perhaps something we could all be reminded of now and again. But it was an amazing observation. And so it was really, and the ability to step out there and say this really bold thing, right? It took almost 400 years for him to be forgiven by the Catholic Church. But what I find poetic about it actually is that in this system that he identified, like I said, with the very first telescope, we may have the first chance of actually seeing life beyond our home planet. And it's in worlds like this one. And so this is the one that I study the most. This is Europa. And so Europa is about the size of Earth's moon, and it has on the outside a giant ice shell that we think is somewhere between 5 and 30 kilometers thick. And I'll tell you why we think that, but when we look at Europa, it's not just what you see, but what you don't see that really matters. If you look at this picture, what is jumping out at you that's missing from every other planetary surface that you've seen? Craters, exactly right. There are no craters. Where else are there very few craters? Or there's not none, but few. It's the Earth, right? So this planet is actually tearing itself apart, remaking its surface on roughly the same timescale that the Earth is doing that. That's truly remarkable. It has the same level of geologic activity as a planet made of rocks. In fact, what's special about Europa is this activity. Those cracks on its surface are tectonic in nature. We don't understand exactly how they work. The reddish materials you're seeing are salts. We don't really understand their chemistry. We are trying to figure out how this planet works by looking at its surface and trying to see below. And so what we've been able to identify, as I mentioned, was this ocean that's underneath it, using its magnetic field and its interaction with Jupiter. So this was explored by the spacecraft that bears Galileo's name in the late 90s and early 2000s. And so that picture from the surface now down into the interior using geophysics also told us that this planet is actually surprisingly more terrestrial than it is ocean world in some respects. You see, in the outer solar system, water is not particularly rare. There are planets mostly made of water. In Europa's case, it's this thin veneer on the outside, which functions very much like the ocean on our planet. It's directly in contact with the rock below, right? And on our planet, we know this is a source of energy, a place where life has existed and perhaps even began at the seafloor. And so when we start thinking about this planet, this distant world, 5 astronomical units away, it's remarkably similar to the things we see on our own planet. And so we're trying to figure out what actually lies below. What's happening inside this ice shell? What's happening in the deep interior of Europa? Is there water inside the ice shell? How does it communicate with the surface? Are we bringing nutrients from the surface down and things from the subsurface back up? And so we're sending entire spacecraft to be able to study that. And that's some of the work that we're doing to understand the geology and the evolution of a world like Europa. And one day, where would we all like to go Well, obviously, at least for people like me, I can't wait to get into that ocean or any liquid water we can find inside the ice shell. And so that actually kind of drove me and my team to start thinking about where we could do these kinds of experiments. And in fact, the Earth is a great place to start. This is a system we understand, it's a place we can go, and we can test the ways that we measure and think about things. So I got started thinking about Antarctica as a way to think about Europa, going to our backyard to go out into space. And in so doing, discover this planet for the first time myself. So as I like to say, I'm new to the Earth. But this is the way I like to think about it. And so here's McMurdo Ice Shelf, which is very close to that first picture that I showed you. It's the US home base in McMurdo. This is the Ross Ice Shelf. This is a floating piece of ice made of glaciers that stitch together that's the size of France. It is planetary in scale, right? And this is Thwaites Glacier, which is a system I'll describe to you in a moment. So we started building underwater vehicles, like this robot ice fin I mentioned, in order to be able to get underneath the ice here and get ready for one day sending these things to Europa. But in the meantime, we might as well take a look at our own planet and try to understand it. And so IceFin has things like science sensors that measure the ocean. So importantly, we measure the salinity, the oxygen, and the temperature. And that actually altogether gives us a fingerprint of the water column. It tells us where the water formed, where it's going, and what it's interacted with, such as melting glaciers. So we can measure climate change in real time. We have sonars across the vehicle that allow us to map the environment. We have cameras because we're humans and we have our eyes connected to our brains. And then we build the electronics inside the vehicle so that we can know where we're going underneath the ice, move around fully in 3 dimensions, and take all of the instruments we'd normally put on a mooring on a 3-dimensional journey underneath the ice. And so what that's allowed us to do is to start targeting systems, not just because they remind us of Europa, but because they're important for the Earth. So this is Thwaites Glacier, and over the last 30 years, we've watched this glacier recede dramatically and collapse. This giant ice shelf used to be a stable feature, and now it's basically going away. And if you can see it now, it's basically a connected set of icebergs. So this massive thing is actually protecting us from a great amount of sea level rise. It's melting at what's called the grounding line, and it's forcing the thickest part of the glacier to be exposed to the warming ocean. And so as that grounding line moves back, it's a place we've never been able to take any data, but it turns out to be a place where robots are really useful. So if you want to get through 30 kilometers of ice on Europa one day, getting through almost a kilometer, 600 meters in this case of ice on Thwaites Glacier, is a nice way to start that. So what we did is to go out with our colleagues, so members of my team are in this shot, members of the BBC, members of our team from the British Antarctic Survey, colleagues from NYU and from Penn State. And this is us standing on that ice shelf, 600 meters below is the ocean. And then we deployed IceFin through this, through the ice using this frame in the background here. So this is early 2020, before all of our lives were about to change. But this is what we were doing in January. And so what we do with IceFin is to put it down through a borehole through the ice shelf, and then allow it to kind of swim underneath. So here's the position on Thwaites that we were going. We take the robot, we put it down through the ice. One day we'd like to melt into the ice ourselves. And then we put it out underneath the glacier and start moving towards these places that we've never seen. And it allows us to measure, like I mentioned, the temperature, the salinity of the water column, the topography underneath the ice. And all of these tell us about what's happening. So what you're seeing here is kind of our walking on the moon shot, which is the very first view of a grounding line of a major glacier. And it's taken, and what you can see is, you can see this ice is full of rocks. It's been kind of ground up as it gets close here. And right here at the grounding line is the first contact of the ice, the ocean, and the glacier. And what's happening here, we can see, is significant amounts of melting. And so we can measure that in real time. And what that tells us, this is data from the vehicle, is that that warm water is making it all the way back here and eroding the glacier like we thought. So this very, very warm water, this is 2¼ degrees above the temperature at which it would be freezing. So it's a lot of heat available to melt this very cold system. But what we also discovered was that inside the cracks is an even more important story, perhaps, which is that these are the places that are melting the fastest. So you remember that picture I showed you of the glacier falling apart? Well, the melting that's happening up inside of these features, which we've never been able to measure before, is actually widening those cracks and making them more unstable. So this is a process we never knew of that we need to now think about as we try to protect our own planet and figure out how long we have to save it, right? Things that we have to do. So I just wanted to share with you that little vignette because it really is the inspiration of distant worlds that gave us the ability to measure things like this. And there's many examples of that in the Carl Sagan Institute, in planetary science, and in earth science, of collaborations between people that think differently that allow us to see things for the first time. And so we're really excited, and I'll just share with you in closing that Europa Clipper launched just a few weeks ago, the first spacecraft that will actually go back and target Europa. And one of the cool things that we're doing there is sending an ice-penetrating radar that was used first in Antarctica out to Europa to be able to measure some of that ice shell that I showed you in the earlier parts of the talk. So anyway, thank you so much for allowing me to be here, and it's been a pleasure.
And so now we went out to the stars, we went back home to our solar system, and now I'd like to introduce you to Bruce Lewinstein, who's a professor here at Cornell in Science and Technology and Communication. And if I ever have a question of how I talk to people or how I best tell my stories, this is one of the people I call. So, Bruce.
Thank you, Lisa. So for those who don't know, the Department of Science and Technology Studies is where history and politics and sociology and anthropology of science are done. And I'm really grateful for the Carl Sagan Institute for including those kinds of topics in what the Carl Sagan Institute does. This is my typical opening slide. I did modify it a little bit today to add that in addition to being in the USA itself is located on Earth, in the solar system, in the solar neighborhood, in the Orion arm, in the Milky Way galaxy, which is in the local group of galaxies, the Virgo supercluster in the universe. And that comes from Robin Hirst's book, My Place in Space. If you don't know that book, I strongly recommend it. My grandchildren will be getting copies of it at Thanksgiving. For me, Carl Sagan and other science communicators like him are my objects of study. I'm interested in understanding what they do and helping others, as Lisa said, do it themselves in the future. So my connection to Carl Sagan, I graduated from college in the early summer of 1980. And my first job was as a science writer working on a series of books about the human body. Our first book was The Brain. And as it happened, just a year earlier, Carl Sagan had published Broca's Brain. And this was therefore one of the things we turned to. I was a researcher for the book. One of the things we turned to find out, well, what's going on? What is current knowledge? And of course, that meant that, there's Broca's Brain. And of course, that meant then that in the fall, as I started work in the fall of 1980, we were watching Cosmos as it came out. I will admit, I didn't see a lot of it in that initial release, in part because I was newly graduated, I was living in a group house with a lot of other recent graduates, and let's say access to television was not the highest priority in that place. But let's jump ahead to the kind of work that I do. So we jump ahead about 30 years, and I was working on a project about the history of science books in the years after World War II. It's a period when we think of science as taking place in journals, and the question is, what role did books play? I won't go through the whole project, but I noticed an interesting set. There were 3 books that had movie or TV shows associated with them. 3 bestsellers, 3 sort of very prominent books that had video associated with them. Jacques Cousteau's Silent World, the book came out in 1953, the movie came out in 1956, directed by Louis Malle. The movie is amazing. Despite more than 50 years of technical development since then, the visual quality continues to grab me every time I look at the video. It's just an amazing movie, the quality. Bronowski's Ascent of Man appeared in the UK in 1973 as a response to Sir Kenneth Clarke's late 1960s series called Civilization, which somehow managed to leave science out of civilization. And Bronowski's goal was to put science back into our understanding of what civilization is. The series was imported to the US in 1974. And Ascent of Man has a direct connection to Cosmos because they were both produced by Adrian Malone, the first one at the BBC, and then after he was forced to leave the BBC because of disagreements with them here in the US working with PBS. That's a different story, I won't tell it. We've heard so much, and we heard the wonderful quote from Kavi Dabala about the inspiration that Cosmos provided. One of my standard tools in classes and when I talk to scientists is to ask them what inspired them to become scientists. And when I talk to people of a certain generation, my parents' generation, let's say, they tell me they read Paul de Cruyff's book, Microbe Hunters, published in the 1920s. If I talk to a later generation, they read Jane Watson's book, Double Helix, published in the 1960s. I see some heads nodding here. When I ask the next generation, they tell me they watched Cosmos. That's what inspired them to become scientists. So what did I notice about these three books? What struck me about them was that they each treated the idea of imagination differently. As presented in broader culture, science is about facts and ideas, not about imagination. And yet, as these two epigraphs suggest, there's an interesting reversal when we think about imagination. With the scientist, the prototypical scientist, Albert Einstein, says that imagination is more important than knowledge. And yet the poet, Wallace Stevens, says eventually an imaginary world is entirely without interest. So I saw that in the three shows as well. In the interest of time, I'll skip over Cousteau and Bronowski in detail, just to say that Cousteau was anti-imagination. Truth was central to him. At one point, he filmed a fake skeleton in a shipwreck. Then he said, quote, "But we did not use the sequence. It was fake. I have no untruths in my pictures." And he sighed when he tried to describe what it was like to be a scuba diver. "I cannot tell you how much better than the imagination it is downstairs." That's how he referred to going underwater. Bronowski wasn't as anti as Cousteau, but imagination was only part of the whole. He was more interested in the rational and the emotional, in adding the cultural component. In the famous opening scene to Ascent of Man, he says his imagination, his reason, his emotional stability and toughness make it possible for him not to accept the environment, but to change it. And that series of inventions by which man, from age to age, has remade his environment is a different kind of evolution, not biological, but cultural evolution. And I call that brilliant sequence of cultural peaks the ascent of man, leaving aside the gendered aspect of his time. And of course, that brings us to Carl Sagan. In Cosmos, imagination is central. It's fundamental. One of the most memorable parts of it is the ship of the imagination. It was the place that let you explore the cosmos. Now, I do have to acknowledge that critics of the show found the setup a little bit cheesy. The version in Neil deGrasse Tyson's reboot was perhaps a bit more acceptable as a sort of future. But this was still an amazing technical achievement at the time. Truth and fidelity were critical to Sagan's vision of cosmos, just as it was for Cousteau and Bronowski. Once, according to one of his biographies, in the middle of a take, Sagan and co-writer and planetary scientist Steve Soter stopped the process because they needed to calculate, literally on the back of an envelope, the amount of oxygen in a planetary moon's atmosphere. Sagan was absolutely committed to getting the science right, recalled one of the show's other producers, Jeff Haines-Styles. But nonetheless, imagination was central to Sagan's vision. There was this blend of fact and speculation. Again, the famous opening sequence, we wish to pursue the truth no matter where it leads, but to find the truth, we need imagination and skepticism both. We will not be afraid to speculate, but we will be careful to distinguish speculation from fact. So, imagination, as well as fidelity, was a key idea in Cosmos. Notably, the fidelity is to science. Although there is culture in Sagan's Cosmos, the series is about the science itself. And for that science, you needed imagination. There was, of course, a straightforward level of imagination, coming up with the amazing explanations and illustrations and animations and so forth to see things that we hadn't seen before. But ultimately, those explanations were not the important thing. There's a different level of imagination that's fundamental here. Sagan said, I would be very pleased if viewers left the entire Cosmos series without remembering a single fact, provided that they found rekindled some of that ancient human joy in understanding the natural world in the celebration of nature. So for Carl Sagan, imagination is key both to Cosmos, the show, and to the cosmos in which we live. Thank you very much.
So thank you very much for taking us out in the imagination. And so what I wanted to do now is, I know if you've seen the program, this is called The Surprise, or A Surprise. And for that, I would like to introduce Captain and Dr. Joe Derway. He is an undergraduate from Cornell. He's a flight surgeon with the NASA Johnson Space Center for over 28 years. He came all the way from Houston up to be with us today. And he has served as a crew surgeon for a multitude of missions, including the shuttle, long-duration international space missions, and commercial crew missions internationally. He's also the co-chair of the multilateral medical operational panel of all 5 agencies on the ISS. And I said it would be a surprise, so I let Joe tell it.
Well, thank you very much, Dr. Kaltenegger. What a great day today, and I am honored to be part of this celebration, and thank you for the invitation. I'm originally from down the road in Johnson City, Binghamton, New York, and currently live here in Houston, Space City. And it's known, and we're very proud that the first word transmitted from the surface of the moon in July 1969 from Neil Armstrong was Houston. Tranquility Base here, the Eagle has landed. So use that for all your Jeopardy games and winnings. And if you haven't been down to Houston, please come down and visit. I would be honored to show you around and some things behind the scenes. I am a graduate of Cornell in 1980, and for the folks here who grew up on iPhones, yes, Bruce and I and others did have cameras around at that point. And as a student, I was here when Dr. Sagan influenced so many of us through Astronomy 101, the Pulitzer Prize-winning book Dragons of Eden, the book Cosmos, and subsequent TV series. And this is a picture of graduation, and I'm also honored that a couple of my fraternity brothers from that era are here to join us today, so thank you very much. Many of us from that generation were also impacted by Dr. Sagan's ability to communicate to the public about our place in the universe and its exploration. My generation and our parents fondly remember the many times he was a special guest on the late night show with Johnny Carson. Dr. Sagan had Johnny and the audience riveted with his poetic and educational explanations of aspects of our universe. And yes, the billions and billions of stars phrase. Carl was truly a part of the fabric of our culture. Many of us at Cornell pursued our careers in part due to his impact. I befriended Dr. Lisa Kaltenegger over the past few summer reunions events here at Cornell, hearing her and others discussing their work and the efforts of the Carl Sagan Institute. This past May in Chicago, Dr. Kaltenegger was one of our guest speakers at the Aerospace Medical Association, our annual scientific meeting, an international group of aerospace medicine and human performance professionals. And I was serving as the president of ASMA, and I had the great privilege of inviting Dr. Kaltenegger to be with us. The meeting included science sessions and guest speakers of the likes of Harrison Schmitt, who walked on the moon during Apollo 17, as well as other astronauts. And during Dr. Kaltenegger's presentation, she riveted the audience with her knowledge, enthusiasm, and elegant delivery as she paid tribute to Carl Sagan and described the work of the Carl Sagan Institute and the scientific discoveries being made. And I must admit, she jokingly did say she's spoken to many, many different groups, but never stood up in front of over 1,700 physicians and other healthcare folks, so bravo. In aerospace medicine, we study the unique physiological, medical, and environmental aspects of spaceflight. Across the range here you see of the human spaceflight program in the US. We care for the men and women who venture into space to perform science and exploration on behalf of all humankind. And this is a picture of us preparing Bob Behnken on the left and Doug Hurley on the right for the first test mission of the NASA SpaceX Dragon mission in 2020. And on the right, Colonel Doug Hurley is actually from down the road in Owego, Appalachian, New York. The magnificent discoveries of the James Webb and Hubble telescopes are mind-blowing. How fortunate we are to be alive now to experience the discoveries they are providing. And the success of the Hubble included humans, astronauts, delivering Hubble to orbit, and completing 5 servicing missions to repair, refurbish, and extend the life of Hubble through extravehicular activity, EVA. Currently, in low Earth orbit is the International Space Station, a tremendous achievement of international collaboration to create a platform and laboratory for science and discovery, including the study of our solar system and our Earth. Not everyone may be aware, but it is incredible to realize that we have had continuous human presence on the ISS since November of 2000. 24 years, a great achievement. History is often defined with special events that mark various eras. For example, the 1400s and the discoveries of new worlds, and names like Christopher Columbus and others that mark that period. So too, our era will be remembered 500 and 1,000 years from now as the first time a human stepped foot on a celestial body in the name of Neil Armstrong. I also believe the legacy of Carl Sagan will be remembered from this era well into the future for the gift that he gave us, and not only looking into what the solar system and looking at the solar system and universe with awe and wonder, but also turning our eyes back upon our planet and encouraging us to be good stewards of the spaceship Earth. And especially for those students here and listening online, looking to engage with a variety of careers within the fields of astronomy, astrophysics, engineering, earth sciences, and yes, even medicine and physiology, your future is very bright and exciting. The world population when Neil Armstrong stepped on the moon in 1969 was 3.6 billion, and now it is over 8 billion. It is estimated that only a small percentage of everyone alive today on Earth was present when the first human reached the moon over 50 years ago. What you will witness in the years ahead with crewed flights, as well as uncrewed telerobotic exploration, will be absolutely incredible. I hope our future scientists and explorers will be enlightened and motivated by the greatness and commitment to excellence that Carl Sagan exuded. Upon this celebration, I would like to share a very special greeting and message for you today. The message was going to come down to Earth from Dr. Don Pettit, who is now serving a 6-month mission on the International Space Station. The recent pace of work on ISS has been packed, and Dr. Pettit was unfortunately unable to record his message in time for today. And he sent me a note at 3 o'clock in the morning, Greenwich Mean It's time, last night to pass his regards, and was sad that he wasn't able to complete it. But I will read the special greeting and words that he was going to share with you today. Greetings from the International Space Station. I'm Dr. Don Pettit, NASA astronaut, currently on a 6-month mission here on ISS. This is my 4th space flight and 3rd long-duration mission. The ISS is our home in space and an incredible platform for scientific investigation, as well as a great example of international cooperation. It is amazing to realize we have had a permanent human presence in space for 24 years, a milestone I believe Dr. Sagan would have celebrated. However, today is to celebrate him, and I wish I could be there to share his 90th birthday celebration with all of you. Carl Sagan inspired countless people worldwide as he shared the wonder of our cosmos, and I know he would appreciate the view that I have from this place on the ISS. He had a gift for communication and sharing the wonders of science and sparking the wonders in others. He cared deeply about our planet and keenly questioned whether worlds circling other stars could harbor life. Scientists throughout the world, including members of the Carl Sagan Institute, are working on those questions with NASA on missions exploring our solar system and beyond, like the James Webb Space Telescope and the recent launch of the Europa Clipper, NASA's new flagship science mission that will investigate whether there are places below Europa's surface that could harbor life. In addition to encouraging us to turn our gaze outward to the stars, Dr. Sagan wanted us to think about life down on Earth. When he convinced NASA to turn Voyager 1's camera back for one last photo of Earth, he changed our perception of our planet forever. That pale blue dot photo taught us that Earth is indeed a small speck in the greater cosmos, vulnerable and very, very precious. Wishing you all a wonderful celebration as you honor the birthday of Dr. Sagan, Dr. Don Pettit, on board the ISS. So thank you, Dr. Pettit. And I want to thank the Carl Sagan Institute for the invitation to participate today. It was a great honor. Enjoy this celebration of Dr. Sagan. We are all so proud that he was part of Cornell University and was truly a treasure to the world. Thank you.
Thank you so much, and we do understand why he couldn't make the trip up to Cornell today, but we hope we'll see him here one other day. And so with this, I would still like to show you some other greetings that we received from different places of this world. The first one being from Jill Tarter, who was the first president of the SETI Institute and a friend, and also the inspiration, to a certain extent, for SETI to look up. She dedicated her life to trying to find signals of other civilizations in the world, or in other worlds. And so we'll have Jill Tarter's words, and then Bill Diamond, Natalie Cabral. They are the current president and scientific director of the SETI Institute. And then I think we have two people that I might not have to introduce, add some of their greetings to.
Well, Carl, we miss you, and we miss you more and more as time goes on. You were always an incredible inspiration for me, but in particular, I learned and gained from your struggle to make your strong desire to have one last conversation with your dad and the reality of the science and your understanding of our place in this universe and in time and in space. You also were the only one of my colleagues with whom I could share the real frustrations and upsets and difficulties and progress at times that we faced with the slash, burn, and poison treatments for cancer that were the norm back in our day. And finally, no one can thank you enough for having brought Ann Druyan into our sphere and all that she has done to help us tell our story and enlighten the world about life and universe and everything.
In the second half of the 20th century and on into the 21st century, few people have had as great an impact and as much influence and have served as such a source of inspiration than Carl Sagan. And today would mark the 90th birthday for Carl Sagan, who left us all too early at the age of 62. But it's fair to say that so much of what we do here at the SETI Institute that he inspired wouldn't be done. We might not even be here were it not for Carl Sagan. Our co-founder, Jill Tarter, and Frank Drake himself worked and collaborated with Carl when they were at Cornell. Many of the scientists here at the SETI Institute come from Cornell University. They were Carl students. They worked with Carl. They were inspired by Carl. And I have met countless people throughout all my interactions in the work we do here at SETI and with colleagues all around the world who became astronomers, who became astrophysicists, who went into science, who became educators because of the influence of Carl Sagan. I was inspired and thrilled at his books, both his fiction and his nonfiction. The movie Contact features Jodie Foster playing Jill Tarter, more or less, in the early days of her work as a SETI pioneer. So from all of us at the SETI Institute, we just want to wish and send our heartfelt congratulations to Cornell and this wonderful celebration of Carl Sagan and his life. A happy birthday from all of us here to Carl Sagan, and enjoy the celebration. Let's all continue to inspire as Carl Sagan did. Thank you.
Hi, I'm Natalie Cabral. I am the director of the Carl Sagan Center at the SETI Institute, and I wanted to wish you a happy birthday for Carl. I think it would be 90 today, so it's been a long time. We are missing him, and so many things have changed in astrobiology since we lost him. But at the same time, we are manifesting his vision of seeing the Earth from afar and using astrobiology as a mirror to try and understand what is our place in the universe and on this planet. And I would say that the value that he put forth really are those that are needed today. So many of us are trying to carry this and move this forward. And I know you are too at Cornell. This is a place where he started and spent his career. We are doing a lot also at the SETI Institute. For me, I had the chance to meet Carl in 1986. I was a freshly minted master student. We spent an hour together at the DPS conference in Paris, and this is a moment I will never forget. That day, he never told me to go to this or that fancy school. He just told me, never let anybody else tell you who you should be or what you should be doing. And this is really something that I've kept until now, and will carry this with me for the rest of my career. So happy birthday, Carl. And on behalf of the whole crew at the Carl Sagan Center, again, happy birthday.
Greetings, Bill Nye here. Happy birthday, Professor Sagan, or if I may, happy orbit of the sun. 90 orbits of the sun would have been an extraordinary achievement. And speaking of extraordinary achievements, thank you for everything you did for all of us here on Earth. I don't know if you remember me, but I took one class from you. I joined the Planetary Society when you sent me a letter in 1980. Now I'm CEO of the Planetary Society, and on your behalf, we are the world's largest independent space interest organization advancing space science and exploration so that citizens of Earth will know the cosmos and our place within it. The cosmos is an idea that you popularized through your whole life. And if you were here, you would realize that per your predictions, Earth's climate is changing on account of the greenhouse effect. And what you alluded to many times is the movement for anti-science, or the lack of critical thinking, is more significant or more influential than ever. And as you pointed out, when we have a society that's increasingly technically complex, the technology, for example, used to record this video on a device that fits in the palm of your hand, as more and more people use these technologies with a smaller and smaller fraction of us who understand them, the more trouble we could be headed for. And this is another prediction you made. So thank you for your predictions, and thank you especially for inspiring us all so that we could, dare I say it, change the world. Happy orbit of the sun, Professor Sagan.
I loved how Carl Sagan could read his audience. He could communicate in your terms, not just his. He certainly spoke in my terms when I interviewed him in 1994. We were talking about the possibility of contacting other civilizations in the universe, and he mentioned that we'd already been broadcasting signals into space in the form of radio and television broadcasts. And this is the way he said it.
MASH is being broadcast to the stars. I haven't gotten the check for that yet. No, the residuals are going to be hard to come by, but I hope that they're getting Mr. Red. If you have a big enough antenna and you have a sensitive enough detector, you can pick it up.
He ignited our imaginations and kindled our curiosity. He was a bright star in the night sky.
So what you heard was music by Joseph Turin, a composer of contemporary American music who's composing for orchestras and film internationally. And he actually made it all the way here to be with us today to celebrate the 19th birthday. So thank you very much for sharing the piece inspired by Carl Sagan with us and being here with us today. And now, I hope you're holding on to your seats, because what we're doing now is we're going to have a look at Voyager's golden record, a view from 81,419,422,572,180 feet by Professor Andrew Hicks, Professor of Music, Medieval Study, and Classics, and he has done the calculation all on his own. So as my very esteemed colleagues at the Carl Sagan Institute, if you find any calculation errors, I had nothing to do with it.
Thank you, Lisa, and please don't check my math. It's really a pleasure and an honor to be here and to share the stage with so many distinguished colleagues, brilliant speakers, all in honor of Carl Sagan. And I want to insert a bit of history into this as well, because more than 47 years ago, in late August and early September 1977, NASA launched the Voyager 1 and 2 spacecraft to study the outer solar system. They are now the farthest flung human-made objects in the universe. More than 81 trillion, etc., feet from our celebration today. Both continue to relay data to Earth, and I suspect that some in this audience may have in fact seen some of the recent news articles about the successful reboot of Voyager 1's S-band radio, which had been silent since Saturn, to fix some of the corrupted code that had in fact hobbled its otherwise strong data transmission. Voyager continues to make headlines even 50 years, or nearly 50 years after its launch. But I'm not here to talk to you about Voyager's incoming transmissions. My focus is the outbound communicative medium mounted prominently on the main body of each spacecraft, doubtless some of the most expensive real estate in the universe. Produced at the mere cost of $18,000, or about 2/thousandths of a single percent of Voyager's total budget, a gold-plated copper phonograph record rides along. Etched into their grooves are approximately 90 minutes of music, an acoustic collage of Earth sounds, spoken greetings in 55 languages, most of them recorded here in Ithaca, and 118 encoded images, the last a typed memo from President Carter, which is perhaps the first time that someone skirted a hard word length count limitation by posting an image of text. This record, Carter writes, represents our hope and determination and our goodwill in a vast and awesome universe. But I'm also not here to pay tribute to President Carter's intergalactic rhetoric, but to the cosmic vision of Carl Sagan, who had been charged to place a message aboard the Voyager spacecraft. And Sagan assembled a remarkable team, including Ann Druyan, who you heard from earlier, and a mere 8 months before Voyager's launch date, they settled on a long-playing phonographic record. And Sagan tells us it was Frank Drake's idea, another Cornellian. It was a brilliant, but hardly obvious spark of inspiration. The extended play record, which spins at 16 2/3 revolutions per minute, was a very old format, introduced in the late 1930s and primarily used for talking records and Muzak-like machines in the 1950s. It was long forgotten by the late 70s. Imagine, for instance, sending a Betamax to Jupiter on the Europa Clipper, because who knows, maybe Chuck Berry has found a new audience there, because you may have heard of Steve Martin's quip, if we hear from aliens, they'll say, send more Chuck Berry. That decades-old format had the benefit, though, of endurance. It was not only long-playing, but inscribed in the right medium, it was long-lasting, impervious to the decay that would destroy any magnetic tape that dared to travel beyond our atmospheric protections. Each record is further protected by a cover that you see here, in fact, that you saw on the wall behind Bill Nye when he was speaking earlier, a cover that's electroplated with ultra-pure uranium-238, an embedded atomic clock that records the record's original release date, at least for the next 4.5 billion years. The cover also bears engraved symbols that you can see that detail how the record is to be played and its images decoded, with a ceramic stylus and cartridge included for free on each spacecraft, like a decoder ring in a cereal box. In the event that Voyager is discovered by intelligent life in worlds unknown, or maybe by future humans, if technology outpaces its modern maiden voyage and the record boomerangs back into human orbits. This cover is itself a record of its own function, its own chronology and its own point of origin, all expressed in an optimistically universal language of mathematics. The phase transition of a hydrogen atom, the decay of uranium-238, and the frequency of pulsars. But the record that it protects is more than a mathematical object. We are feeling creatures. That's what Sagan wrote in Murmurs of Earth, an account of the record's production published by Sagan and his team in 1978. The inclusion of music uniquely enabled by the phonographic medium offered, he writes, quote, a credible attempt to convey human emotions. Perhaps a sufficiently advanced civilization would have made an inventory of the music of species on many planets, and by comparing our music with such a library, might be able to deduce a great deal about us, close quote. In writing this, perhaps Sagan had in mind Alan Lomax, whom the Voyager Interstellar Record Committee had consulted on the final selection of music. For Lomax was a prominent ethnomusicologist who had developed an ambitious cantometrics project, as he called it, which inventoried and measured global musics to correlate the variety of musical styles to diverse social organizations and socio-psychological factors that Lomax thought would surely shape habitual musical practices. It is characteristic, though, of Sagan's expansive imagination that he recast Lomax's project as a potentially intergalactic study conducted by unknown intelligences. But Sagan's cosmic vision rested on ancient authority. Quote again from Murmurs of Earth, the connection between music and mathematics has been marked at least since the time of Pythagoras. But so far as we can tell, mathematical relationships should be valid for all planets, biologies, cultures, and philosophies. As an intellectual historian, I can't help but hear in Sagan's claim the resonance of a nearly identical sentiment expressed in the late 17th century by Christian Huygens, an astronomer and mathematician best known as the inventor of the pendulum clock and the discoverer of Saturn's moon Titan. In Huygens' posthumous publication Cosmotheoros, or Cosmic Visions, Huygens envisioned an intellectual and philosophical kinship between ourselves and unknown planetarians, as he called the probable inhabitants of other worlds. Quote, geometry is of such a nature that its principles and foundations must be immutably the same in all times and places. It is the same with music as with geometry. It is everywhere immutably the same and always will be so. So Sagan's mathematically confident posthumanism has had a long history. But Sagan knew this too, as did the entire team that compiled the record. For included as the first sonic encounter in the Sounds of Earth collage is a computer-synthesized sonification of the music of the spheres, the orbital velocities of the planets in our solar system realized at Bell Laboratories by Laurie Spiegel. And I should add that she is, in fact, the only named female composer on the record, the named female composer on the record. And I offer this not as a criticism, but just to mark, as I think Carl Sagan would himself, that the Golden Record is a record of its time. And if we listen now to Spiegel's Harmony of the World, we cannot help but hear echoes of piercing air raid sirens, an acoustic reminder, perhaps, of the Cold War politics that also echo in President Carter's words that are imaged on the other side of the record. We are attempting to survive our times so that we can live into yours. Spiegel's digital sonification encodes the planetary data that was published in Johannes Kepler's 1619 Harmonicae Mundi, or Harmony of the World. So it is yet another unfolding or infolding of humanity's most future-forward, far-flung effort back upon its long historical imagination. Kepler is best known for his articulation of the 3 laws of planetary motion. I won't quiz you on it now, but often forgotten is that he devised those laws in a hunt for a mathematically proven musical universe. For Kepler's laws issue from a contrapuntal planetary science, with Earth, Mars, Venus, Jupiter, Saturn, and Mercury, as you see here, all singing their own tunes in their variegated orbits. And Kepler's music has now, literally, mounted again to the skies. For the music of the spheres has reverted again to a data stream, now etched as a waveform within the copper substrate of a long-playing record, now more than 81 trillion feet from Earth. The golden record is a monument to humanity, imperfect though it may be. It is a gambit on post-humanity, unanswered as it may be. And it is but one of the many testimonies to the legacy of Carl Sagan, who lived a life of science, imagination, and humanism well beyond the scale of the human. Thank you.
Thank you very much, Andrew. So, you might wonder what can inspire curiosity and combat misinformation in these times. So, for that, we should ask Mark Savary. For this, we should ask Mark Savary, and I should know Mark's name because he is the driving force behind the outreach that we do here at the Carl Sagan Institute. He's also a senior lecturer in neurobiology and behavior and science communication. And I would love for you to reimagine the Sagan effect.
Thank you, Lisa, and thank you very much for the invitation. It's an honor to be here and celebrate Carl Sagan's 90th birthday with all of you. So one of my roles is to be the director of the investigative biology teaching laboratories, and in that role I teach nearly 1,000 students every year, teaching them the scientific process, science literacy, and critical thinking skills. I'm also the co-founder of the Science Communication and Public Engagement undergraduate minor that I will tell you a little bit more about. So I wanted to start you with a question. How do you measure the influence of a scientist? Think about that for a moment. Is it the number of publications, the impact factor, congressional hearings, invited talks? Scientists have such a broad impact on students and non-technical audiences, the public alike. And Carl Sagan, little did he know how much influence he had on a high school student behind the Iron Curtain in the late 1980s. I'm from Hungary, and because we were in the socialist bloc, we did not have the Cosmos series on TV when I was growing up. But somebody in 1990 translated the Pulitzer-winning book, The Dragons of Eden, to Hungarian. And I just could not wait until my classes were over in high school to read the next chapter. And it was a mind-blowing experience. It's about the evolution of intelligence. And as you heard from many today, this was one of those books that put me on the path to become a biologist. And there are some other ideas in this book that I still use in my teaching nowadays, like the value of curiosity and the scientific method to understand the world, which is pretty much the definition of science, or advocating for public understanding that I still use in my teachings with my science communication students. So, do you have a book that inspired you, either by Sagan or by others? Raise your hand if you had a book that has inspired you. All right, many of you, fantastic. So, clearly I'm not alone here. So, when I came to Cornell, I was a PhD student here, and I was a field scientist, a field ecologist. I was trained as a field ecologist. Science communication and public engagement was not part of my education whatsoever. It wasn't encouraged. My advisors didn't require that. Despite that, we had fantastic storytellers at Cornell. If you think about Anna Comstock in the late 1800s, wrote about nature. Carl Sagan, of course, was a fantastic storyteller. And I really enjoyed this quote from him because it's so powerful, that public understanding of science is more central to national security than half dozen strategic weapon systems. And yet, my PhD education did not require any public engagement. And later on, I learned that one of the reasons for that was the Sagan effect. And the Sagan effect is a negative thing. According to some, Carl Sagan was not admitted to the National Academy of Sciences in 1991 because his colleagues thought the Cosmos series, his books, his public engagement was fluff. It's not something that scientists do. And even now, you can see that from Susanna Martinez Conde from 2016 that this concern still exists among scientists. Having public engagement, science communication, part of your job is not really appreciated very often. So now close your eyes and imagine for a moment that there is a world where every scientist is valued when they share their knowledge openly with the passion of Carl Sagan. Wouldn't that be beautiful? And that's exactly what we are trying to create here at Cornell and at many other higher education institutions nowadays. Because undergraduates nowadays are not like how they were 20 years ago. They are developing their science and science communication identities at the same time. So science communication is no longer an afterthought, rather an integrated part of their education. And our role as instructors and educators is to create these opportunities for our students so they can learn about science communication and public engagement, and they can follow Carl Sagan in his footsteps. In the Library of Congress archives, I found this syllabus by Carl Sagan on the left. The title was Critical Thinking. As you heard previously, Carl Sagan really focused on critical thinking education. And just recently, Christina Schmidt and myself and many other colleagues developed a critical thinking online module that now hundreds of students every semester take this online course, and they are explicitly exposed to critical thinking teaching at Cornell. Similarly, Carl Sagan was very interested in science literacy. This quote from the demon-haunted world says, "The consequences of scientific illiteracy are far more dangerous in our time than in any that has come before." And unfortunately, it's still true nowadays. But we have strong and powerful tools, such as discipline-based education research and evidence-based pedagogical practices, to come up with good methods to teach science literacy to our students. So, for example, just recently published this paper with my education postdoc, Joseph Rouge, when we discuss how we can teach science literacy, and we have data for the past 10 years to showcase that it's working. Similarly, we can develop science communication classes where our undergraduates become storytellers. We developed this class with Kitty Gifford in 2017. Many other colleagues here at this institution and other institutions develop similar courses. And students, undergraduates, can pick up skills so they can become scientists, but in the same time they can become science communicators. They can gain these skills and apply these skills to engage the public. And because so many of us were thinking on a similar level, in 2020, with Bruce Lowenstein, Kitty Gifford, and many others, and Lisa Kaltenegger, we developed science communication and public engagement undergraduate minor. And Ann Druyan sent us a nice note when we did this, and you can read the whole quote in the Cornell Chronicle, but it says the shorter version, Carl, consummate scientist and peerless communicator, opened the way. It's fitting that Cornell University is assuming a leadership role by offering a minor in this vital field. Thank you, Ann, for the nice words. And now, if you go to the Carl Sagan Institute website, you can find the astrobiology minor and the science communication minor right next to each other. I think this would make Carl Sagan really happy. And we have over 40 students in this minor. You can see some of them here. They are all scientists, and they are learning about science communication and public engagement. As you see on the left, Kitty Gifford. Behind Bill Nye, the science guy, Professor Lowenstein is hiding there. And these are fantastic students who are interested in science communication. And just to mention a few of them, Rachel Lewis, she took our science communication class at Shores Marine Laboratory. She's a marine biologist, but now responsible for public engagement at Shores. Annie Loza, he was a neurobiology undergraduate here at Cornell, took our class, science communication class, in 2022. He graduated with a minor on his diploma, and then now he's a writer for STAT. And last but not least, Gillis Laurie, who took our science communication class as a first-year student and graduated this year with the astronomy major and science communication minor on her diploma. And of course, she's one of the co-organizers and the public engagement coordinator for this event. And of course, in the first class, I still remember, although it was 4 years ago, we went around and everybody had to say a fun fact, right, all the students. And when it got to Gillis said, well, the fun fact, I was born on the same day as Carl Sagan. So happy birthday, Gillis. So with this undergraduate education, we are really hoping to not just inspire curiosity like Carl Sagan did, but also fight misinformation, which is very important nowadays. And these students are developing the identity of a scientist and a science communicator at the same time. So I would really love to have the Sagan effect to be something positive now and not negative. Maybe something like scientists are influencers who receive training in public engagement early in their careers, because that is how they become well-rounded scientists. Thank you very much.
And so you've heard from some of the senior people here at Cornell and at the Carl Sagan Institute. And believe me, it's really, really hard to pick who gets to speak today because there's so many exciting things to talk about. But the Carl Sagan Institute, to me, is also the institute of 1,000 voices because of the amazing students and postdocs and undergrads who come through our doors and who help us for part of their time make this a vibrant, interdisciplinary, and incredibly engaging community. And so, while we don't have all the time in the world to tell you about all the student endeavors going on here, the next person is gonna talk about laser sailings to the star. It's Josh Umansky-Castro. He's a PhD candidate in aerospace engineering here at Cornell Engineering. Josh?
I figured I'd start with my favorite Carl Sagan quote. I'll give you a moment to read it. This is actually printed on board the circuit boards that will be flying to space on this mission that I'll talk about shortly. So my name is Joshua Umansky-Castro. I'm a PhD candidate in aerospace engineering, and I'm part of the Space Systems Design Studio. We're a lab in Cornell Engineering under Professor Mason Peck. The lab's been around for about 20 years now. And we are known for modeling, designing, building, testing, and even flying new spacecraft technology. And we're especially known for student-led projects. Students have the fortunate opportunity to design, build, and fly their own spacecraft as part of this lab. One of which I want to draw your attention to on the left is called a ChipSat. This is essentially condensing the essential elements of a larger satellite on a single circuit board that fits in the palm of your hand. And I have a sample of the one I made here for scale. So these types of satellites are not as capable as bigger satellites, but they enable new forms of space exploration, some of which I'll talk about shortly, like light sailing. So light sailing is a concept that's been talked about for about over 100 years now, but has only been really brought to life in recent years. And it's been talked about by scientists, including Carl Sagan, who helped bring it to popular audiences through The Tonight Show with Johnny Carson there. And the concept boils down to propelling spacecraft through light. Let's say you have a light source such as the sun, or an artificial source such as a laser. The photons emitted from those sources can bounce off this sail like a shiny reflective sheet kind of flying through space. And each of those photons will provide a small push that will drive this sail. And that small push might not be much, but in the vacuum of space, it can add up. You're going to keep that momentum, and it'll accumulate with each of those small pushes. With a big surface area like those sails, you can get small pushes that will get you faster and faster, and eventually get to destinations further than any spacecraft has gone before. So in recent years, they've finally been able to bring this to life through JAXA that did a flyby of Venus. NASA has done a few deployments in low Earth orbit. The Planetary Society, founded by Carl Sagan, even launched their own in 2019. This is LightSail 2, which is very successful. And there even was one that launched this year and is currently in orbit right now. So in comparison to those, the sail that we're developing here at Cornell is a little smaller. It's 0.5 meter by 0.5 meter, and it's called Alpha, so there it's on the far left with a person there for scale. And despite its small size, it is still capable of accelerating to higher speeds, if not faster than the existing sails to date. And that ties back to a few factors, one of which is those chipsats that I mentioned. When this sail is driving a payload that's only a few grams, it does not need to be as large. And because of that, the sail itself can be more durable. The mechanism that helps it stow in the rocket and deploy and unfold into space can be simpler too. So we're using a really interesting origami mirafold and a shape memory alloy cross-framed to help this expand into its fully unfolded state once it's in orbit. Finally, the sail material itself is retroreflective. So that's the same as what you see in stop signs or bicycle reflectors. It directs light back in the direction it came from, and that allows us to control the direction of the sail with the direction of the incoming source of light, such as a laser. So laser sailing is particularly exciting because of the idea of going interstellar once again. There's a group out there called Breakthrough Starshot that is bringing this to life, and their idea is to have a large phased array of lasers that will send a fleet of light sails to the Alpha Centauri system in the hopes of looking for signs of life out there. And to do that, it has to be a very strong laser beam, accelerating these to 20% of the speed of light for a 20-year journey. And to get something that fast, you also need a small sail and a lightweight payload that will be something very similar to the chipsats we're developing here at Cornell. They sort of rebranded it as a star chip, but very similar concept. We are not quite there yet. The work here at Cornell is a little kind of near term in terms of our own solar system exploration, but our chipsat sail architecture is looking at first Earth orbit and then moving on to Moon and Mars exploration. And I put near term in quotes because each of these does take a very long time to get launch ready, and we're still very much focused on the Earth orbit part here. And you'll see there's a few spacecraft in the picture. So the sail, like I said, does not get sent to space in that state. It does have to go in another spacecraft to deliver it. And the one that we're using is called a CubeSat. If you haven't heard of them before, CubeSats are cube-shaped satellites. They're about 10 centimeters tall, and here's one for scale next to us here in the clean room. And this form factor allows for very accessible and affordable launches. There's even an initiative called the NASA CubeSat Launch Initiative that will launch these for free for some universities, and we're launching through that. So this form factor is stackable. There's different units based on the standard U unit size, and it allows for rapid prototyping. The bulk of our satellites actually are 3D printed, which is really cool. There's 2 missions that we're working on that involve CubeSats here at Cornell and light sails. So there's one called Alpha that's been in development since 2016 and will be flying this summer. And against better judgment, I started a new project in the 5th year of my PhD called Sailing to the Stars. Very dreamy name, but similar concept, testing the deployment of light sails from CubeSats, but inside the International Space Station instead of outside. And this allows us to get high-resolution footage that will be live-streamed from astronauts that will be conducting this deployment sequence. So the concept of operations for both is very similar. I'll focus on alphas here, but it will be ejected from the International Space Station and have a random tumble. It'll stabilize into a spin, and when we establish radio contact, we can send a command to have it eject and unfold from the CubeSat. So it's sort of a nesting doll of different satellites. We have our chips on the sail on the cube from the space station. A lot going on, and there is a lot of engineering that went into this. I don't have time to cover it, but I just figured I'd show all the parts, the thousands of parts, and the thousands of hours that went into designing these spacecraft. One thing I do want to focus on is this idea of sort of a pre-interstellar message plaque. We're not quite going to the stars yet. But on board our spacecraft, we have holograms that are mounted to the solar panels. These were based on sculptures designed by the artist C. Bangs. And it's inspired by the work of Carl Sagan, the Pioneer plaques and the Golden Record. And it has a central theme of DNA. And you can see the double helix of the DNA there in clay form and holographic form. And We were fortunate enough to do a collaboration with the Intrepid Museum in New York City, where we got to showcase these. And we even had an extra hologram on our sail of the Voyager Golden Record, or the Voyager spacecraft overall. So these holograms, we want to inspire a larger audience to think about what messages could we send to the stars. And in that theme of Breakthrough Starshot, one day going to the stars, there's actually a really cool functional purpose of these holograms. We could have a holographic light sail that not only provides these interesting images, but can actually help stabilize the sail while riding on the laser beam. And I won't go into the engineering behind that, but just take my word for it for now. So picture a holographic laser sail that can be composed of thousands of images of artwork throughout history, people, places, things around Earth. It's a really holistic representation of life on Earth that we could send to the stars. And we really want to encourage the public to think about, if given this chance again to go to the stars, what could we send? Finally, I want to acknowledge the big team behind me here. I've had the pleasure of working with over 100 students across the College of Engineering, Arts, and Sciences since I've started here, and I could not have done this alone. It's been a personal dream of mine to build and send something to space, and it's been an honor to share this experience with so many other aspiring engineers. Thank you.
Thank you, Josh. And the key point here is you see how much work goes into all the different pieces that you get to see snippets of today. And you've heard a lot about what we're doing with spacecrafts and trying to get to the cosmos. And you also heard how it links back to our own planet. And so I would like to take you into the lab and into the early times of our planet, and then back out to rocky worlds out there that they are so hot that anything might melt. And for that, I'll invite Jonas Bieden up here, who is a postdoctoral fellow at the at Astronomy and the Earth and Atmospheric Science Department, who will tell you how hard it is to make these things reality.
Hi, everyone. 3 years ago, I'm going to be honest, I didn't know Carl Sagan at all. And as soon as I arrived here in the United States, I get to know him and everything he has done. And more recently, I had a discussion with Gillis, who organized this event, and we were amazed by how inspiring Carl Sagan was, and especially that even today, people are getting to know him, just like me, and I'm sure I'm not the only one in this audience. So one of the things Carl Sagan was working with is infrared light, and infrared light is actually amazing to look at heat. And I'm going to talk about that hot topic of the day, and because I'm working at the Carl Sagan Institute on a very curious question, which is, what are lava worlds made of? So let's dive into the realm of hot, scorchy, rocky world. So picture yourself at the surface of an exoplanet that is actually covered with magma. It might look like the video you are seeing there. It's like very hot, very inhospitable. You wouldn't stand any minute on this planet, of course. But it is fascinating, and we found a few examples of them here by NASA, but actually, a decade ago, the Kepler mission exposed thousands of lava worlds. So it's unique, but not kind of rare. I like that picture because even if it is a little bit outdated, each dot represents an exoplanet. And each red dot is actually a planet that has a surface temperature high enough to have molten rock at the surface. And that's basically the definition of a lava world. It's so hot that the temperature can melt rock, and you can picture that all over the surface of the planet. And today, researchers are trying to understand what they look like, really. Do they have an atmosphere or not? Do they have like one side of the planet fully molten and then the other side very cold and raining rocks? Or do they have different dynamics? Do we have convective cells within the mantle, or do we have any other type of convection? It's basically, if you look at the video on the left there, it can show different regime. Do we have like a very cool, smooth, dark, and lightly bubbly surface, or do we have like a very eruptive type of behavior with a lot of outgassing and bubbling magmas? But finally, we are trying to characterize those planets because they actually have secrets that we cannot unravel on Earth. Because there are no occurrence of lava world in the solar system. But the thing is, lava worlds are basically the beginning of the story. It is at the beginning of the formation of a planet. And with that, we can actually understand a few different things, how the tectonic plate is putting into place, how it started, or even the composition, how the magma crystallized and formed the core, the mantle, and the crust we all know today. It is also at the beginning and maybe putting all together the building blocks for life to thrive after the cooling of those magma oceans. And one of the things that is critical to understand and to link all those parameters, all those things together, is actually the temperature and the composition. So to understand those and have slight answers to those questions, we need to ask the expert about the composition of lava world. Maybe not that one, but we have an amazing tool that helps us to understand and observe those planets, which is the James Webb Space Telescope that everybody knows of. And the thing is, with those observations, we kind of need some backup measurements and benchmark experiments to better understand and how to interpret the observation of that telescope. And that's how I come in. I basically reproduce a lava world, but in my lab. We need those experimental experience to understand those observations. And so the setup we build here at Cornell University is the one you see on the picture now, and it's kind of very basic. First, it's unique in the world, and with that, we can actually melt planets in the lab. That's cool, I like it. And it's basically three simple instruments. We have the heating stage, that's where all the fun is happening. That's how we control all the parameters of our planet. And then we have a microscope to actually look at the sample, but also having the microscale information of those samples. And then we have the spectrometer, which is basically the infrared detector and gathering all the information we need, the physical properties of those planets. But the only thing we're missing in this is the sample that we are putting in the setup. We cannot go to lava world, obviously, so we need to back up a little bit and come back to Earth and use whatever we can find on Earth. So what scientists do is going to the field and collect lava samples, just like the video is showing. And as soon as we have done that, we can bring back the samples to the lab that looks like this. And after a few preparation that I'm doing, we end up with small chips. And those chips, we actually control the composition. And those chips represent our lava world. Well, right now they are cool and they form a rock. But as soon as we put in the setup, we can actually heat them and form a magma. And at the end of the experiments, we end up with that kind of results. Without going into details, we basically observe the physical properties of those magmas. And what you can see is the red curve is very different from all the other curves. That means the physical properties of the magma is very different. And these results are linked to the composition and the structure of the magma and the temperature as well. So that's how we can actually connect the observation of James Webb Space Telescope and have insights about the composition of those planets using laboratory experiments like this. So unfortunately, I have no full answer to give you yet concerning the question, what are lava worlds made of? But I'm going to go back to the lab and do more experiments to give you those information. But I would like to end up my talk with the quote of Carl Sagan, which is, "We make our world significant by the courage of our questions and by the depth of our answers." Carl Sagan believed that multidisciplinary research is actually crucial to have breakthrough in science. And he thinks that the laboratory is not a physical space, but rather a concept where all the perspective and diverse ideas are converging to actually expand our knowledge and our understanding of the cosmos. Thank you.
And so it's my pleasure to now ask another question. And I have to say, ever since Elaine Petrov, who's a professor of mechanical and aerospace engineering here and also a fellow of the Carl Sagan Institute, sent me her talk title, I was intrigued. Because what she's talking about is, can alien elephants fly? And I would really like to know.
So this is a talk about building instruments to detect life in our solar system. And the idea of life in our solar system for me was really inspired by Carl Sagan, by his books, by Cosmos. It taught me that it's not only plausible, but it's likely. It inspired my career path, and I'm so honored to be here today and to be a faculty member at Cornell. And Carl Sagan having been here was something that really drew me to Cornell. And so I was looking at the other talks and the faculty that are here today. I'm so proud. I'm sorry that I wasn't able to have him as a colleague, but all of the other people that he drew in, from the students to the faculty that you've heard today, they're inspiring as well. And I think this day is really a testament to that as well, to him. So anyway, we'll go on talking about finding life in the solar system. So if there's life in the solar system, where is it? We could look at every one of our planets and many of the moons, like we've already heard about today, and we can imagine, as Carl did, what life might look like there. We don't have time to do that today, so I thought it would be nice to start by focusing on Jupiter and remembering what Carl imagined life could look like there today. So I should be able to play this video. Okay. Let's see. Does that work? No. So I'll just tell you, I guess, a brief summary. Maybe you all saw this. Oh, they can
What would life elsewhere look like, even if it had an identical molecular chemistry to life on Earth, which I very much doubt? It could not be similar, very similar, in form to familiar organisms on the Earth. The random character of the evolutionary process must create elsewhere creatures very different from any that we know. Think of a world something like Jupiter, with an atmosphere rich in hydrogen, helium, methane, water, and ammonia, in which organic molecules might be falling from the skies like manna from heaven, like the products of the Miller-Urey experiment. Could there be life on such a world? Well, there's a special problem. The atmosphere is turbulent, and down deep, before we ever come to a surface, it's very hot. If you're not careful, you'll be carried down and fried. So one way to make a living is to reproduce before you're fried. Turbulence will carry some of your offspring to the higher and cooler layers. Such organisms could be very little. We call them sinkers.
I'm going to pause it there. I could just sit here and watch the rest of that video. I encourage everyone to. But Carl goes on. This was really transformational to me when I heard these ideas from him, and I thought, this sounds plausible. There's something he says at the end of that video, which I wanted to read, because I think this is really powerful without watching the whole thing. He says, "The study of a single instance of extraterrestrial life, no matter how humble, a microbe would be just fine. would de-provincialize biology and show us what else is possible. So that's what I'm really inspired by. It doesn't have to be something so grand. I'd love to be part of just finding a microbe somewhere else. And towards that idea, I want to take us further out in the solar system to Saturn, which we haven't visited yet today, pretty sure. Specifically to a moon of Saturn called Enceladus. Many of you are very likely familiar with Enceladus. Many of us believe that it's one of the most exciting places to look for life in our solar system. And so scientists are hypothesizing with evidence now about what life might look like there, just like Sagan did for Jupiter. And so one idea of what it might look like is these little green, they don't necessarily have to be green, it's a microscope view, image of bacteria that live at the seafloor and subsist on CO2 and create methane as a byproduct. And those bacteria and the other organic matter that's part of their ecosystem could potentially be transported from the seafloor to the plumes, actually far above the surface, and actually forming the ring around, part of the ring around Saturn by these geysers that are constantly erupting. And so there's a diagram showing how that might happen. This work is, these hypotheses are influenced by the science that was done by the Cassini spacecraft, much of it done here at Cornell and is still being done at Cornell. Cassini visited Saturn, many of its moons, including Enceladus. And when it visited Enceladus, it flew through its plumes, which I think is just still incredible to this day, from the first time I learned it. And another thing that's incredible about this is it flew through the plumes at 14 kilometers per second or 30,000 miles per hour. And when it flew through the plumes, it stuck out an arm that was on the spacecraft to collide with the particles in the plume. So that collision happens at 30,000 miles per hour and measure the ejecta of that collision. So what happens when you hit something at 30,000 miles per hour? Luckily, none of us have ever experienced that. But we know, because we can reproduce it in the laboratory or just even studying high energy impacts, what would happen. So any ice is vaporized. Any solid particles, if they're there, are pulverized and broken up into their atoms and molecules that make them up. And this impact is so violent that it even breaks apart the atoms and the molecules and knocks off the electrons and leaves many of them in a charged state, or otherwise known as ionized. And so that means those ionized particles are the ones that we can detect with our instrument. Here's an example of some of the particles that are found with the instrument. What was found was the largest organics to date outside of Earth when Cassini made this measurement at Enceladus. Some examples are shown here, and actually here's a plot. Looks like squiggly lines, but to explain, these are molecules that scientists can pinpoint and identify, and many of them are organic in nature, going up to about 2,000 AMU. So 2,000 AMU, how big is that on the scale of organic chemistry? There's a few people in the audience who maybe know from their classes. I didn't until I started doing this work. It turns out this is actually peanuts compared to the elephant scale molecules that drive our biochemistry and our biological processes. So the best that scientists can do is try to reverse engineer what the larger biomolecule might have been coming out of this impact. So we see things like common hydrocarbon structures. We see things like phosphate, which is the backbone of our DNA. So could it have come from something more complex? Potentially, but to know that is to have to solve something like a 1,000,000-piece puzzle where all of the pieces were never in the box to start with. So having this information, this led some of us to question on my research team, is there a better way that we can make this measurement? If we're able to go back to Enceladus or some of these other places in the solar system, is there a way that we can more gently interact with the plume or other parts of the environment that we are sampling and keep those biomolecules intact? Well, one source of inspiration is how we do that on Earth. We don't obliterate everything at 30,000 miles per hour. We have other techniques. And one technique that I'm particularly passionate about has been around since the 1990s, and it is the gold standard for measuring and analyzing biomaterial. It's called electrospray ionization. It was invented, or at least for this purpose, invented by a professor of engineering at Yale named John Fenn. He won the Nobel Prize for this work because it's been so impactful. And what John Fenn did with electron spray ionization is he found a way to extract what he called molecular elephants from samples, biomaterial, and give them wings or make them fly so that they can be detected by an instrument. This is not John Fenn here in the video, but this is a video that I thought did a nice job explaining how electrospray ionization works. So you can go ahead and play it, and if you're able to go to about like the 35-second mark, that would be
ideal. In this video, I'm going to show you what an electrospray is and how electrospray ionization works. It is the bridge that connects molecular biology and electronics. How does it do it? It starts by applying a high voltage to a droplet. Ions suspended in the liquid migrate to the surface of the droplet and accumulate in the area where the electric field is more intense. Normal droplets are rounded due to surface tension, but with the ions accumulating in the surface of the droplet, the electrostatic force pulls the liquid surface out. When the voltage is high enough, something remarkable happens. In this case, at about 6 kilovolts, the electric forces equal the surface tension and the droplet turns into a cone with an extremely intense electric field at the tip. A microscopic jet emerges from the tip of the cone and breaks into ionization.
Okay. Can we go to the next slide? Perfect. Okay, so I wanted to show some data. I don't know, this mic is... Let's go to the next slide.
In this video, I'm going to find that in the liquid migrate to the surface of the droplet and accumulate in the area where the electric field is more intense. Normal droplets are rounded due to surface tension, but in this video, I'm going to show you what an electrospray is and how electrospray ionization works.
All right. Now you all know how electrospray ionization works, I hope. So I wanted to show this plot from a scientific paper. If you just type electrospray ionization into Google Scholar, you'll get over 1 million results. This is one I dug out of there, where they were studying bacteria like the ones that we could hypothesize could exist in the environment of Enceladus. And so this is a plot that indicates all of the proteins, the very large organic molecules that were able to be isolated and detected with an electrospray ionization instrument. And you can see here by looking at the y-axis that those mass values range from about 10,000 AMU to 100,000 AMU. So we're talking hundreds of times larger than Cassini was able to detect. And if you're able to detect proteins like this in a sample, that's sort of like a fingerprint. And there's been, these libraries built by the decades of research that have been done that would be like a fingerprint for this type of life existing. So the next question is, okay, this is a really cool instrument. How do we build one that we could put on the spacecraft? And that's the question that my research group has been trying to answer for the last couple of years. Thanks to being a researcher and a faculty member here at Cornell, I've had the privilege to work on this problem. This is one of the first projects that I started new at Cornell in collaboration with the Department of Astronomy. So if we want to build an electrospray instrument for space, we have to change some things based on the new operating environment. I don't know if this video will play. This is a video of an electrospray source that we build and fire in our lab. We have many of them. This is one of the ones that's easy to see. And this is a picture on the left of a subset of the research team that's contributed to this project so far. It's also involved many undergraduates and master's students. These are the more senior researchers. So some of the questions that we're trying to ask through our research is, what should this instrument look like to be able to detect large organic molecules in the environment of a planetary surface or a plume? We have two hypotheses for what we think might be successful designs. The first is to pursue the idea of developing a vacuum electrospray ionization source. So we no longer have the privilege of the atmosphere to operate in, and also the privilege of having expendable resources like gases that are used in ground-based systems. And so to design an electrospray source that operates without those resources, we need to rethink the geometry and we need to rethink the operating fluid. So that's what we're doing in this research program. And you don't really need to worry about the details, but there is an image of one of the sources that we've been playing around with in our lab to get preliminary data. So this is one idea. Another idea is to explore the idea of desorption electrospray ionization, or the DESI approach to making this measurement. So in this case, unlike all of our other electrospray sources, our sample doesn't have to be mixed in with another fluid and sprayed to liberate those molecular elephants. Instead, those molecular elephants can live wherever they were naturally found or can be put on the solid surface and then impacted by an electrospray ion plume, and we measure the ejecta from that process. So we're exploring both of these design avenues in our work. I want to summarize this research effort. So far, we have not had instruments in space that could detect large organics. But because of the instruments that we have, we now want to go back and look for them. The ground-based gold standard, state-of-the-art for analyzing large organics is the electrospray ionization mass spectrometer, and in the green arrow shows the mass range that it can cover. And then I wanted to highlight a few of the biochemical structures that exist across this mass range. So at the low end, we have a molecule like histidine, an amino acid. Every one of us has many of these in our body. Everything else is built from these amino acids. So we go up from there. So we have, going up in an order of magnitude, a DNA pair. Then we have proteins like hemoglobin all the way up to mRNA. These exact structures we may not find in other places in the solar systems, but if we can find things of analogous complexity, it would be a very strong indication that there might be life in that location. So I want to end with this quote from Carl Sagan, that there are as many atoms in one molecule of DNA as there are stars in a typical galaxy. And I hope that I will be invited back for his 100th birthday celebration, and I can say something about the instrument that I think would allow us to detect these complex molecules in the clouds of Jupiter or in the plumes of Enceladus. Thank you.
And so the next person I would like to introduce is Bas Barstow, and he's professor of biological and environmental engineering here at Cornell. But he's also the person that if you ever see him on campus, try to get him for 5 minutes. If you sit down with Bas for 5 minutes for a cup of coffee, you have 5 new papers that you're working on somehow, all of them incredibly important, incredible fun, and incredible unsolved so far. So either be careful meeting him on campus or try to corner him in a quiet minute that he probably never has. But he also sent a really intriguing title. If you were permitted only one question to ask them. And so I was wondering if you knew about the unanswered question or not.
Thank you, Lisa. I was told this wasn't proper English. But if you bear with me to slide 4, maybe we'll get there. And I hope this advances. Oh, here we go. So I'm afraid Lisa might throw me off if I go over by even a second. So I want to make sure that I acknowledge I'm representing a team here. It wouldn't be possible without these people and probably a lot more on top of it. I'd like to put my lab's work in the context of the Drake equation. In the late 1950s, Frank Drake came up with an estimate for the number of civilizations that we might observe in the cosmos. Since then, astronomers like Lisa have started to constrain some of the early terms, starting on the left-hand side of the equation. Lisa said that I'm a biologist, and you might think I'm going to talk to you about the probability that life will emerge on a planet. But I'm actually much more interested in the last 2 terms, particularly the last one. How long does a civilization last? And this question is not really about aliens. It's really about humanity. And it's so important that when Ellie Arroway, the heroine of the movie Contact, when she was asked if you could ask the vegans, not the vegans, by the way, if you could ask them just one question, what would it be?
And she chooses, this is her question, how did you survive your technological adolescence? You know, you can think about it. There's so many ways a civilization could come to an end. Nuclear war, climate change, you name it. But turning back the clock on technology, I don't think this is the answer. We know that life expectancy, if there was a single metric for quality of life, I think this is probably it. We know this takes money, right? And money takes energy. So an imperative, I think, of any responsible government is to increase energy availability. But if we do this the traditional way with fossil fuels, we're going to cook the planet. You could imagine an even more advanced civilization than our own increasing energy use even further and increasing its quality of life even further. But how do we do it without wrecking the planet? I think we're in luck. In the 1970s, the physicist John Barrow predicted that as societies advance, and I wrote the word mature here, and I realize this is a really bad choice of word. I think it's a really terrible choice. But as they become more advanced, not only will their energy use increase, but the precision with which they control matter and energy will also increase. And this sounds a lot, when I read this when I was a teenager, I thought this sounds a lot like biology. And in fact, science fiction got there before academic science. Down below, there's a couple of my favorite examples from science fiction. If my mom is watching on the live stream, I think she'll recognize these. Nature gives us a great existence proof for this. Photosynthesis channels something like 130 terawatts of power into biomass. And this is 6 times the power use of civilization today. This is truly incredible. And it also gives us all these amazing capabilities for catalysis, material synthesis. When we do that, and it does this with almost no human intervention at very, very little cost, thanks to self-assembly. So my lab thinks that applied biology could revolutionize energy in the way that it's already revolutionized medicine, starting in the 1930s and going on till today. But harnessing this potential is difficult because we don't understand weird biology nearly as well as we should do. But I'm going to talk to you today about 3 examples where I think we've made some progress in the past few years. First one is biomining. During this century, we're going to have to build a new sustainable energy infrastructure. It will be full of things like electric vehicles, wind turbines, solar panels, nuclear power, superconductors, you name it. It's going to require a stupendous amount of metals. If we get these through the traditional route, and I've shown it on the left in red, we're going to despoil our planet, probably just as much as we will through climate change. But if we can harness metal and mineral interacting microbes, we might be able to build a much cleaner green route, I'm showing on the left, called biomining. But we don't know nearly enough about weird bugs that can interact with metals and minerals to do this. But we've made a little bit of progress. So we were able to understand how the microbes Gluconobacter oxidans and Shigella onadensis are able to first get metals, rare earth elements. These are used in wind turbines, EVs, superconductors. Get them out of rock, and then how Shigella could separate them into pure elements. We made so much progress on this. 2 of my students, Sean and Alexa, were able to start a company called Regen to commercialize this. Second, let's just say we do build the sustainable energy infrastructure and we electrify most of our society. We're still going to be left with well over 1 trillion tons of CO2 in our atmosphere that will be warming the climate, potentially for tens of thousands of years to come. Nature naturally removes this CO2 from the atmosphere, but it does it far too slowly for our tastes. We could accelerate this again by microbes that dissolve olivine, the most abundant element in the entire solar system, and then transform it into another rock, magnesite,
On top of this same process could also liberate enormous amounts of elements we need for sustainable energy technologies. So myself and my colleagues, especially Esteban Gatzel, Sarah Krebs, and Michael Charles, we're building the microbe mineral atlas to figure out how we can accelerate this process with engineered microbes. Next, let's say we electrify as much as we can, we capture CO2. There are still going to be loads of applications left where we need hydrocarbons, but we won't be able to get them from photosynthesis. We want that for a beautiful world, making foods that we enjoy. Instead, I'd love to build a microbe that can eat all this renewable electricity and CO2 and turn it into complex molecules like jet fuel. We know nature can do something like this, but again, we don't know nearly, or we didn't know nearly enough about the physics and the biology of this process. As a result, I didn't know if it was worth starting the enormously demanding feat of genetic engineering required to pull this off. So, my lab figured out the mechanism and the physics, the biology behind electron uptake, and we were able to build a new model of this process that predicts it could be much, much more efficient than photosynthesis. Now, to take advantage of this potential, traditional genetic engineering is not going to cut it. The technology we have today for engineering is far too slow, far too expensive, and doesn't scale nearly well enough to let us take advantage of all this new knowledge that we're acquiring. So, two of my students, three in fact, David Specht, Bryce Brownfield, and TJ Shepard, built a totally new way of doing genetic engineering that relies on molecular DNA uptake. It's called natural competence. What it does is it allows us to do genetic engineering much cheaper, much faster, and scale much further than traditional technologies. Again, they've advanced this so far that they've just started a company called Forage Evolution to commercialize this. I also want to dwell for a second on the question that Lisa posed to me when we first met 5 years ago, I think. And she said, say there is an alien civilization that's used synthetic biology to sculpt its biosphere, to solve climate change on its own world. What would it look like? I'd like to try to answer that question. All of this energy use, I recognize that many of you might think the idea of increasing our energy use, given what it's done to our world, sounds scary. I think I'd be remiss if I didn't acknowledge that. But I don't think it is. Right? Humans today, I think, care more about their environment than they ever have done in history. And I bet future humans or advanced aliens will care even more. So I'm betting that our future will look way more like the image on the left than the one on the right. As a result of this, we may not see aliens because they've chosen to preserve the beauty of the cosmos. They might be hiding in plain sight. They've created a world that looks natural, but in fact is deeply advanced. I want to end this with some reflection on how we might actually pull all this engineering off. And I'd really like to come to maybe my favorite part of Contact. You know, it's the contrast between Ellie, the dreamer, the visionary scientist, and Drumlin, maybe the villain of the movie, the arch careerist. And every step of the way, Drumlin takes advantage of Ellie. But we know, if you look through history, right, breakthroughs in science and technology, they need dreamers. They need weirdos and misfits like Ellie. And so we have to ask ourselves, how does the academic system today create and hinder opportunities for them? How do we create opportunities for more people to do exciting, impactful work inside and outside of academia? And there's one last thought I want to leave you with. There's loads to play for here. There's a century's worth of innovation. So we shouldn't handicap ourselves by short-term thinking. Thank you very much.
And so I know you probably understand why it's never a 5-minute coffee when you start talking with us. But as you're saying, we have so much to do, but I hope you also saw through all of the work that we do here at the Carl Sagan Institute, we always look back at our planet because this is our home and we want to safeguard it. And with our view outwards, we always also have a view backwards. And so let me still take you out a little bit into the universe for the last 2 contributions we have. And so the next person is Rebecca Payne, who was a postdoctoral fellow here, but is now a professor at Bate. And she will tell you about planets at the edge and maybe the possibility for space dinosaurs. And she comes from a background of geology. Rebecca?
Hi, thank you so much. Very excited to get to talk with all of you today and share in all of the amazing research and art and inspiration that we've been talking about, inspired by Carl. And so from that, I want to set the stage for my research and where I fit into the multidisciplinary wonder that is this field by bringing back this picture, this pale blue dot that we've been talking about a lot. And this amazing pixelated, grainy, fantastic image is an amazing context for what astrobiology and searching for life elsewhere in the universe is like, but it's also important for giving us an excuse to stop and look back at our own planet and how much we can learn from it, because that dot represents not only us in the moment that this photo was taken by Voyager, but it also represents everything that the Earth has been, everything that it could be, and it gives us an excuse to ask questions like, well, that little dot, what can we learn about it now, but what would that dot look like if we move it somewhere else, or if its position around our sun changes, or if the sun is a little brighter, or if the life living there is different. And so my research is asking questions like that. It's wondering, well, okay, let's change a little bit about that pale blue dot and see how much more we can learn about our place in the universe. So for instance, one example of that, and I think a useful context for it, is thinking about the Earth as a perfect example of a habitable blue dot. And we have that thanks to the fact that where the Earth happens to be located is capable of sustaining liquid water. And the habitable zone is a region around a star that we can define as a place around that star that can sustain liquid water. If we move a planet a little bit too far away where it's getting less sunlight, eventually you get to a point where no amount of stabilizing climate feedbacks will be able to keep it warm and from freezing over. Whereas on the other end of that, if you move it a little bit too close to the star, you start to boil your planets, which is also not great for life. So if we take a planet like the Earth, say, and put it around a different star, how much does that change? And some of the research that I did with Lisa while I was a postdoc here at Cornell was asking questions like that, taking an Earth-like planet and putting it in orbit around a much dimmer, redder, more quiet M star, and looking at how the Earth's climate changes and what we could use to try to figure out what a star and a planet system like that would be like. So we did that with a planet called Speculoos 2c, which is a rocky, approximately Earth-sized planet in orbit around a quiet M star. And we looked to see if you put an Earth in the position of Speculoos 2c, what potentially could that climate look like, and how much could we learn using tools like the James Webb Space Telescope about its atmosphere. And so from that, a lot of my work, as you'll see from any plots that I show, a former colleague of mine called them spaghetti plots, and that is exactly what they are. It's many, many plots of colorful lines that resemble spaghetti, and these spaghetti plots give us lots of exciting information. So for instance, with Speculoos 2c, you see an atmosphere where up at the top, that top row of 3 charts looking at how the atmosphere would look to a telescope like the James Webb Space Telescope. We can see that if you put the Earth in orbit around Speculoos 2, it looks kind of like the Earth. We see a lot of water and a lot of other exciting gases, but it's hot. And it's quite possible, as we look at the lower set of 3 charts there, that it would be even hotter than the Earth by a significant margin until you get to the point where you're boiling your oceans. We don't know for sure if Speculoos 2c is just beginning to heat up or if it has fully boiled away any water that it may have had. But just from looking at light like we would looking at the pale blue dot that is the Earth, we could learn that kind of information about its atmosphere, about its history, about what Speculoos 2c has gone through, using the light that would come from its own pale, insert color here, dot. And so we can get a lot of cool information just from looking at that sort of place in the universe and how our planet can inform us about others. But we can also get interesting information about our own pale blue dot just thinking about how it has changed over time. The Earth hasn't stayed the same throughout the entirety of its history. And in fact, one of the biggest things that has changed what the Earth looks like is life. So one way to think about that, for instance, is over the course of Earth history, the complexity of life and what life was doing on the planet has changed so drastically that the composition of its atmosphere has been changing over time as well. The spread of trees on the continents, where prior to that it was a planet covered in algae and moss, plants figuring out how to stand up and have stems fundamentally changed the atmosphere from a largely oxygenless world to a very much oxygenated world. And the lovely atmosphere we have to breathe is thanks to plants figuring out how to evolve to stand. And continents moving and splitting has had just as big of an impact on the composition of our atmosphere. And we can use geologic records like the record of trees conserved in charcoals to reconstruct what oxygen has looked like over the course of Earth history. And then from that, we can make more spaghetti plots to figure out what the atmosphere's composition would look like over altitude and how its temperature would change, so what its climate would look like. And from there, we can think about the Earth from an alien perspective. If we had this kind of information about the Earth at different points in Earth's history and how it's changed over time, where each of those spaghetti lines is representing essentially what the composition of the atmosphere or its climate would look like at a different time slice in the last 500 million years of Earth history, then to an alien, you can see a little bit about how the Earth's atmosphere has been changing over time. And more specifically, you can see how certain gases that are really significant and relevant to life, especially things like oxygen and ozone and methane, how those really biologically significant gases have changed over time may have been, in potential ways, a lot easier to see during some of those big evolutionary leaps in Earth's history. When plants first learned to stand up, the Earth had never seen something like that before, and the influx of oxygen into the atmosphere means that we had probably more oxygen in the Earth's atmosphere then than we do now for a brief period of time. And that was not too far away from when dinosaurs were roaming the Earth, and part of why dinosaurs may have been around was because of those evolutionary advances, because there was so much oxygen available that you could support having huge animals roaming around the surface of the Earth. And if that's the case, if we have a world that could sustain different kinds of advanced life, maybe not with the ability to use radios, but still with the ability to leave their mark on the planet, then one potential question that's worth thinking about as we're going through all of this is what those markers are like. Each of these different graphs here is just showing, again, to a distant observer, as if, for instance, if you were looking at the Earth over time with the James Webb Space Telescope, there are these instances of time where you could see a lot more oxygen and a lot more methane in the atmosphere marked by those different changes in life. And so bringing it back to that pale blue dot, when we're thinking about the Earth, the amount of information that we can get from it and what kind of questions we can ask, it's not just what the Earth is like now, but we can think about what the Earth was like in the past, what it could be like in the future, but also maybe the people that are advocating for the planet at the time, maybe it's not us who will be sending enthusiastic messages into space, but maybe instead something else living there that's just as visible, but just a little bit different, but no less enthusiastic. So thank you very much.
And so with that, I would like to get us to the last talk of the day, and then we have some closing remarks and another surprise at the end. So the last talk of the day is by Lydia Coelho, who is by training a microbiologist, and she is a 51 Pegasus Fellow. It's a very important fellowship that you can get awarded, just very few people do in the US. And she will tell you about her work of looking for colors on other worlds.
If you saw me running around the room throughout the whole day, and if I annoyed you, I'm sorry. I was covering for the Instagram. But just to finalize that, it's such an honor to be a speaker in the Carl Sagan's 90th birthday. I gotta tell you, coming from Portugal, I've never imagined I would be here presenting science to you today. And today I'm going to be talking about my mission in life, which is to search for the colors of life on Earth and in the cosmos. But let's start with the cosmos because that's a little bit easier. So let's jump right into I think my biggest inspirational sentence that I actually used it in the first page of my PhD dissertation. And it's obviously a Carl Sagan phrase. And it reads, "All civilizations become either spacefaring or extinct." To a lot of folks, this calls to space exploration in the sense of Mars colonies and a colony in the moon landing, manned missions, and that's fair, but to me it has a different connotation. I started my path in science as a microbiologist and a cancer researcher. And it was very clear to me at the beginning how bottlenecked we are in our fundamental knowledge of life, of cells, of diversity, of disease. And I believe a lot of this is connected with evolution, obviously. And I believe that a lot of these questions can be answered by looking into space. If we find another planet with life in the same stage as Earth, maybe the life will be the same, maybe it will be different. That itself will give us answers. If we find a planet with life at the beginning, that will shed some light into the origin of life. If we find a planet at dawn of civilization, that will shed a light on our future. We can try to find one of these planets, or we could try to find them all. And so the way we do that is trying to look either into our solar system or outside of our solar system. And I think that's a very Carl Sagan idea of us trying to not be contented in fields and to bridge. Let the solar system folks trying to talk with the exoplanets people, and at the same time with biologists, geologists, and all that. So in the solar system and in the exoplanets, outside of the solar system, we have to think differently when we try to find life. In the solar system, we have a problem with sampling because, unfortunately, in terms of civilization, this is it. It's quite depressing. So if we try to find life, we have to think of microbial life and unicellular life. So we are kind of limited in our sampling. But we have almost no limitation in the tools we can use to sample and to search for this life. You've seen Elaine Petrow's talk, you've seen Brittany Schmidt talk, you've seen the amazing instruments that are being built for us to go close to, for instance, to the icy moons and try to find life there. Now, this is the solar system, great toys, poor sampling, but if we think about exoplanets, the instruments we can use are always lenses, is always telescopes. Sure, we can build them bigger and more potent, and we are doing that, and James Webb has been giving us so much, but nonetheless, it will always be a telescope. But in terms of sampling, there's no limitation. You can imagine any type of planet, any type of life, any type of stage of life, and that is the best laboratory for a scientist, where our imagination has no limit. So to build this together, bring the solar system and the exoplanets together, I love this work from Carl Sagan, from '93, where they took advantage, Carl Sagan and their colleagues. You know, Carl Sagan has this habit of turning around the spacecraft to look at Earth. So they leveraged Galileo mission, the Galileo spacecraft that was en route to Jupiter to study the icy moons. It was actually the spacecraft that gave us data to understand there's water in Europa. And they had this idea, let's also probe Earth, because how are we going to find life if we don't have the most important thing on an experiment, the control? How are we getting this information if we don't know how a planet looks like, if it has life? So through the data of this spacecraft, they were able to look at Earth and understand what we knew, that we had gases in our atmosphere, and the atmosphere itself already shows us that this planet is habited. So it was able to show us it has oxygen, water, CO2, and this is already a reference that is used for people trying to find life or trying to characterize exoplanets' atmospheres. Now, this is very interesting for the atmospheres, but me particularly, I love figure 3. So in figure 3, we are able to actually see something that is beyond the atmosphere. We can see a signature of the surface. We can see a signature of life at the surface. This is a signature of photosynthesis. And looking at Earth, the spacecraft was actually able to give us a hint that we had forests and greenery and chlorophyll. So this itself is a reference that we can now use to search for other planets in other systems that would have this greenery, that would have these forests. But life is not only green. And this is the base of our work in the Carl Sagan Institute, building on this idea of these signatures, of these colorful signatures. For instance, photosynthesis can be purple. There is these purple photosynthetic organisms that do photosynthesis in the dark. So instead of actually using light from the sun, they are going to use heat. So part of the research I do in the Carl Sagan Institute is going on these expeditions where we try to find these other microorganisms, we sample them, and we bring them to the many labs of here at Cornell that are part of the Carl Sagan Institute. You have biolabs, you have remote sensing, and we all work together. So I bring the samples to the biolab and I grow these microorganisms, and then I take them to the remote sensing lab and I measure their spectra so that then we have all the data we need to build databases of planets. In this case, we built a database of purple planets that now people looking through the telescope can compare to if they find planets that are purple and likely if they would have life. But it's not only green and purple we have so many colors. Even ice that people think is inhospitable looking and kind of transparent, actually you can find many, many colors in ice. We built the first color catalog of life in ice with more than 80 colors. You had your orange, your yellow, your green, and many more. And these are all, again, colors that can be used, again, for reference for us to try to find icy exoplanets with colors on the surface. And this Arctic research and ice research brings us to another of Carl Sagan's passions, which was Earth, and trying to make the world see, and this is in '85, what we were doing to our planet. So this is a screenshot of the video. I'm not going to play it, but please search it, where Carl Sagan is teaching the Congress about the greenhouse effect. And if you see it, he's really giving a lecture. It's amazing. You can see the professor in him. But after explaining about the greenhouse effect, he gives us a sentence that will haunt us for the next decades. And that says, the solution to this problem requires a perspective that embraces the planet and the future, because we are all in this greenhouse together. So in my research, I also try to bring this into light. My last expedition was to Svalbard. I stayed in the northernmost settlement where we have the fastest rate of ice loss. One of the reasons we have this ice loss is these colors that you see in this ice. All these biopigments produced by microalgae are accelerating the rate of the ice loss. Make no mistake, this is not the fault of the microalgae. But nonetheless, it's something that needs to be measured and monitored. So in this expedition, we made sure that we measured all these colors of the changing Arctic, of a changing planet. These measurements will allow the scientists looking back at Earth to create models to monitor ice loss through the colors. But at the same time, will allow us that are trying to search for life in other planets to try to look for signatures of change, because a changing planet is by itself a biosignature. So I would like to leave with this note that here in the Carl Sagan Institute, we have all these databases of biopigments that we are building and have been building for a while, starting with the amazing work of Lisa Kaltenegger, that is also an inspiration for me. And I would like to leave with this note on how, in my work, I am also greatly inspired by Carl Sagan's idea of never being stuck in one field. Do not just be stuck in the solar system. Do not just be stuck in exoplanets or biology or geology. Talk with each other and try to mix that. But at the same time, while you are searching for life in the cosmos, try to search for a solution for our planet. Thank you.
And so with that, I would very personally just like to add my thanks to the team that made this possible before I give the word to Ann, who will set up the last two contributions we have for our celebration for Carl Sagan today. I want to thank all of you for coming and joining us, and Linda Glazer and Tricia Berry and Gillis Laurie for their amazing work making this work. Of course, their teams too, and the other students who were helping way beyond of what they were supposed to do. And so thanks everyone for making this an amazing celebration, and I'll invite Ann back up to the stage to tell you the last two contributions that we would like to leave you with today.
Thank you.
To all the speakers, thank you so much. I've learned so much from your talks, but also had this sense that Carl lives in every one of them, in this institute, in the people around the world who love him. You know, losing Carl was, for me personally, a catastrophe that I can't even describe. But what has comforted me throughout these nearly 30 years are a couple of things. One of them is on the Voyager record. So on that record, one beautiful day in June, I asked Carl if I were to meditate while hooked up to an electroencephalogram, measuring and recording all of the impulses from my brain as I thought, and an electrocardiogram, registering my heart sounds, and my rapid eye movement, and everything, every signal I was sending. Was it conceivable that the putative extraterrestrials of our imaginings could someday intercept one of the two Voyagers and possibly decrypt this message within the message of what I was thinking? And with his exquisite smile, he looked down at me and he said, "1 billion years is a long time, Annie. Go do it." So within days, I was at Bellevue in New York City, and I was ushered into a room which had a computer that was enormous. I'm sure it didn't have the computing power in each of our phones, but it was very impressive, lights blinking on and off. And then I was taken into this tiny cubicle in which all light had been prevented from penetrating. And I was blindfolded, and I had earmuffs on. And I lay down on a cot, and I thought for an hour. And to the best of my limited ability, I tried to tell the story of the Earth as we then understood it in 1977, and the story of the origin of life, and the story of the evolution of human beings, and the story of the invention of agriculture, and how that changed us when we moved inside and no longer wandered in little bands. And I wasn't sure how much was an hour because my eyes were closed. It's very hard to measure that. And so at the end, I permitted myself a moment of personal reflection. I thought about my family, my grandparents, whom I loved, my parents, who had been such excellent parents to me, had loved me so well, and prepared the way for my beautiful, wonderful life. And this was about a week after Carl and I had first expressed to each other how we really felt about each other. We'd known each other as friends and even as colleagues on another project for 3 years, but we never dared express to the other because we were both committed to other people. But in this moment of reflection, I meditated, newly fallen, truly in love, with, in my view, one of the most alive and enlightened people who had ever lived. And those thoughts, those feelings, my heart, my brainwaves, they are the most distant objects ever touched by human beings. And they have an estimated shelf life of 1 to 5 billion years. And so in some sense, Carl really is immortal. And how many times have I put myself to sleep imagining the interception of that spacecraft? I never permit myself to imagine what the extraterrestrials look like because I have so much respect for nature. And I know it's completely beyond my imagining. But I only see the shadow of a great spacecraft, the shadow looming over the tiny little Voyagers, spindly little spacecraft that we were able to create within 20 years of Sputnik and launch. So think of it. 1957, we launch a metal ball into near-Earth orbit. It's amazing. What a revolution. And 20 years later, we are launching interstellar spacecraft that behave flawlessly and give us our first reconnaissance of the outer planets and moons of our solar system, and then teach us what the shape of our solar system is as we move through the Milky Way galaxy. We have a very steep learning curve as a species when we put our minds to great purpose. And that's what gives me hope that we can find our way out of our current predicament. And Carl's life is another source of that hope. And in addition, Carl lives through our children and grandchildren. It's my joy to introduce another speaker who will speak to us on this big screen. She is our daughter, Sasha Sagan, who wrote a book that I love deeply called For Small Creatures Such as We. Her exploration of how the rituals and holidays that we have received from our ancestors really have a scientific basis. And in addition, it's her account of growing up in our family with Carl and me as her parents. And after that, we'll let Carl speak for himself.
Hi. I simply can't believe that my dad would be 90 years old. It's astonishing to me, partly because he was so young still, when he left us, and people who die young are frozen in time, but also because he was so timeless. He was so prescient about so much of what the future would hold that when I read his words and remember our conversations or see videos of him, it seems impossible that he has been gone since 1996. He was so frighteningly right about so much of our modern society, about our relationship with technology, about the importance of education, of critical thinking, what happens when we don't learn critical thinking, what happens when we don't get a proper science education. He was so right about our superstition and about our confirmation biases. And I feel so deeply that not just me as a daughter would be so grateful to have him, and so much, it would be so meaningful and so important to have him in my own life, to meet my children, to see me as an adult. But how badly I wish that he were here for the good of the world, that his message, the way he spoke, the way he taught, the way he communicated could be part of the conversation in this precarious time, perhaps above all else, about climate. He was an amazing person, as I'm sure anyone watching this knows that he was, as a scientist, as a science communicator, as a writer, as a speaker, but he was also really amazing as a dad, and a very sweet and funny person. People sometimes ask me, what don't people know about your dad? He was so well known. What do you think people don't know about him? And I always think there was a certain silliness about him that maybe if you only saw him on TV, although you can kind of see it in some of his writing, and I don't know, it's one of the many things I miss about him, and what I carry with me from the 14 years that we had together, from the time I was born until his death. There's so much, but one of the greatest lessons and the greatest gifts that he and my mom gave me was the idea that science isn't just a list of formulas and equations to memorize, but it is a method, a pathway to understanding. And it's not just that it's evidence-based and has these error-correcting mechanisms that make it so special. It's also the source of untold wonder and awe about our place in this grand universe. And you don't have to compromise that spine-chilling thrill, that tingling feeling that we are part of the enormity, part of something greater than ourselves. We don't have to give that up when we try to have a philosophy that is based in evidence, based in science, inspired by nature as revealed by science. And when I think of him and remember him, I miss him dearly, but every so often I get to meet someone who was born maybe even after his death, who just discovered his work and just started reading it. Or sometimes someone writes me an email to say that they named their child after him. And I'm filled with hope that his work and his message carries on, even though he's not here anymore.
And with that, have a really great evening. And in case you wanted to go and see what happened with Ellie and the contact screening, the Cornell Cinema at 7:30 will screen Contact, and there might be another cupcake. And then in the evening, the Fortis Observatory will be open for some stargazing in case you want to see some of those stars. And you won't see the planets, but you can see some of the stars that we have been talking about. Thank you all for coming and celebrating with us.